Hello and welcome to complex analysis. So the topics that we're going to talk about, this will be an interesting course or presentation. Introduction to complex numbers, functions of complex variable, elementary complex functions, complex integration, series in the complex plane, residue theory and applications, conformal mappings, harmonic functions and Laplace's equation, and finally advanced topics. Some of the few advanced topics. Chapter 1, Introduction to Complex Numbers. So, at first, a review of real versus complex numbers. What is the difference? What are real numbers? Real numbers are numbers that can be placed on a one-dimensional line. They are single values, in other words, such as a divided by b, a and b being rational numbers. By the way, rational numbers are also a subset of real numbers. Just like natural numbers are a subset of rational numbers. So a and b are rational numbers. Divided together, one over the other, they become real numbers, with b, of course, different than 0, because it is in the denominator. Examples: 3 divided by 7, 4 minus 9, etc. Or irrational numbers that cannot be written in fraction, such as square root of 2, pi, and Euler's number, which also you can identify or express as the exponential. Complex numbers. A complex number is a number of the form z equal a plus ib, where a and b are real numbers, so they are within R, and I square equal minus 1, that's the complex part. Actually, it has been a concept developed in order to fix a problem, okay, such as the square root of minus 1. Square root of minus 1 cannot be solved. So they made up the concept of going into a different dimension, so to speak, or a different universe, rather, and replacing minus 1 with I square. This is how this square root of minus 1 or minus a negative value becomes solvable. Okay, so this is what they came up with. A is the real part of z, the complex number. B is the imaginary part, because whatever value is multiplied by I is imaginary. If b is equal to 0, so there's no I within z, then z becomes a real number. If a is equal to 0, then z becomes purely imaginary, without a real part. In mathematical operations, combine like terms, so set real part on one side and imaginary part on another. Such as for addition subtraction, a plus bi plus c plus di is equal to a plus c apart, that's the real part of z, plus b plus d times I. b plus d is the imaginary part. In multiplication, okay, now remember, I square is equal to minus 1. So a plus bi plus times c plus di gives you ac plus adi plus bci minus bd, because bi times di gives you bdi square, which is minus 1. So ac minus bd, that's the real part, and ad plus bc, that's the imaginary part. The conjugate is flipping, okay, that's a number denoted by z bar with an overline. That is the value of z, but instead of plus, okay, between the real and the imaginary part, you have the minus. This is called the conjugate. And the modulus is actually the length of the vector-like number, okay, because you see a is, because imaginary and real parts, you can imagine them as being two axes, just like x and y. So the x-axis would have the real part, the y-axis within the space would have the imaginary part, okay? So a and b are the values of 2 points, or I'm sorry, the two coordinates of 1 point. Actually, the first point is the origin, and the second point is a and b for the complex number, You connect them together, you get a vector. The distance from the origin all the way to that point, which has the coordinates a and b, is actually the modulus, which is square root of a squared plus b squared, which is Pythagoras' theorem. In a clearer perspective, so again, a complex number is represented geometrically in 2D space, unlike real numbers, okay? So it is in 2D. You see, a real number is only a number, either on the x-axis or y-axis. This is what is unique about the complex numbers. They are 2D spaced values. So it is one value, but two coordinates, so to speak, which is counterintuitive. How you can have a single value, but within a 2D space. This is what defines uniquely the complex number. So for the complex number, it has a real part associated with the x-axis, as you see here in the picture. This is what makes this clarification about why a complex number is 2D. And you have the imaginary part, the imaginary value is associated with the y-axis. So let's say you have z equal a plus bi. How you represent z is the following way. You have a is the value on the real axis. So a alone is a real value. Why? Because it is one-dimensional. You see, it is represented on one line. But z has both a plus bi, a and b. A on the real axis, which is the x-axis, by the way. B is on the imaginary axis, the y-axis, and this is z. This is the complex number. Now, as we mentioned before, the modulus is, by the way, denoted by two pipes, like the absolute value almost, of z is the distance from the origin, just like vectors, all the way to the point z, which is, by the way, what? If you remember Pythagoras' theorem, okay, the hypotenuse square is equal to the first side square plus the second side square, right? Breadth, or like tread and rise, the tread square plus rise square, or breadth square plus height square. Thus, r is equal to the square root. So r square is equal a square plus b square. R then is equal to the square root of a square plus b square, which is also written as z in two pipes. Now, tan theta, so this is what defines a complex number. The length, which is the distance from the origin, and the angle, or also called the argument, which is theta, is equal to, going back to trigonometry, you know that tan theta is equal to opposite side, which is b, correct, divided by the adjacent side, which is a. Then theta, the angle, is equal to tan minus 1, or arctan of b divided by a. And also another formula for that is the Moivre formula, which is z is equal, so z can also be rewritten as r ei theta, where r is actually this distance from the origin, or the modulus of the complex number, and theta is the angle with the real axis, or the x-axis. Consider two complex numbers such as z1 is equal to a plus bi, z2 equals c plus di. Of course, a, b, c, and d are real numbers, and I square equal minus 1 for any complex number. The addition and subtraction, how they would look like. z1 plus z2 is equal to a plus bi plus c plus di. Again, you set the real parts, or the real values, on one side, and the imaginary values, which are any value that is multiplied by I, is an imaginary part, an imaginary value. So the real values are a plus c, that's the real value of, the outcome vector or complex number, plus b plus di, b plus d is the imaginary value of this new number. So a plus c is the real part, b plus d is the imaginary part. In the same way, z1 minus z2 is equal to a minus c plus b minus d. A minus c plus b minus d. We rearrange the number into real and imaginary parts. Multiplication, again, remember I squared is equal to minus 1. So z1 times z2 is equal to a plus bi times c plus di equal ac plus adi plus bci minus bdy plus bi times di gives us bdi square, which is minus bd. Then, so what you get is ac minus bd, so the real part on one side, and plus ad plus bc times I, which is the imaginary part on the other. The conjugate is z bar is equal to a minus bi. Now, what are the conjugate properties? This is an important number, by the way. Z times z bar is equal to z squared, the modulus square. Why? Because z times z bar gives us, let's say, a plus bi times a minus bi, okay? Which gives you a square minus bi square, b square, I square, but I square is minus 1, so a square plus b square. You can try it yourself, okay? Now, the conjugate of a sum is also the sum of the conjugate. So, z1 plus z2 bar is equal to z1 bar plus z2 bar. Conjugate of a sum is equal to the sum of a conjugate. That's important, okay, when solving a problem like that. And z1 times z2 bar is equal to z1 bar times z2 bar. So the conjugate of a product is equal to the product of conjugates of each complex number. Division. When you have two numbers, complex numbers that are divided, such as z1 divided by z2 is equal to a plus bi divided by c plus di. But we want to get the real and the imaginary parts of this number, which is z equals z1 divided by z2, correct? How to do that? We need to multiply by the conjugate of the denominator, both on the upper side and the lower side, meaning we need to multiply both the numerator and the denominator so that we won't change the value of the complex number. We cannot just simply multiply the denominator. It will change the overall value, correct? So you multiply both numerator and denominator, and this is how we get rid, because you remember z times z bar gives us modulus of z, which is square root of c square plus d square, okay? So what you get is, for z1 divided by z2 is ac plus bd plus bc minus ad times I. That's the imaginary. Actually, the imaginary part is bc minus ad divided by c square plus d square I. And the real part is ac plus bd divided by c square plus d square. Don't forget that. Okay? So, reciprocal is simply the inverse of z, okay? Now, 1 divided by z is actually equal to 1 divided by z times z bar divided by z bar. If we multiply both numerator and the denominator, we can get rid of the imaginary part in the denominator so that we can set apart the real and the imaginary parts, by the way. Almost the same thing we did on the upper example, except here you have the inverse instead. So, which is equal to z bar divided by z modulus of z square is equal to a minus ib divided by a square plus b square. The real part would be a divided by a squared plus b squared, and the imaginary part would be anything that is multiplied by I, which is minus b, divided by a squared plus b squared. Remember, the denominator is a common value for both the real part and the imaginary part. Polar form, so z equal, okay, this is the polar form, which is important. Z can also be written as equal r times cosine theta plus I sine theta, or also r e I theta, which is the Moivre theorem. Actually, we're gonna see it again in the next slides. So r is equal to the modulus of z, and theta is the argument of z, or arctan of b divided by a, of the imaginary part divided by the real part. Going back to polar and exponential forms. So let's say you have z equal rei theta. According to Euler's formula, ei theta, where the radius is 1 here, a special case, is equal to cosine theta plus I sine theta. If r is different than 1, then you simply multiply both ei theta by r and also cosine theta plus I sine theta together within parentheses by r. As a reminder, this is the representation of a complex number. You have a, b. These are the coordinates of z, which is a point, and also it has a length, so it acts like a vector. The length or the modulus of z is actually square root of a squared plus b squared, and the argument of z, which is theta, is the angle here, which is arctan b divided by a. Complex numbers addition is like vectorial addition, meaning that z2 starting from z2 starting origin, when you have z1 plus z2, okay, so z2 starting origin is z1's endpoint, so both together make a longer vector, okay. So z2 starts or begins at the heels of z1. The origin of z2 is at the heels of z1, so they make a longer vector when added. Now, complex numbers multiplication not only scales but also rotates the resulting complex number. Why? Because, as you see, for when we multiply both vectors like z1 and z2 in this case, you multiply the modulus, so it scales the length of the outcome vector. But not only that, also for the arguments are added, which are the angles of z1 and z2. When you add the angles, you are rotating the vector. That's why the multiplication not only scales but rotates the two vectors that are being multiplied. Because as you see, argz is equal to argz1 plus argz2. Why? Because if you go back to the exponential form, rei theta multiplied by, let's say, r2 ei theta 2 gives you r times r2, so you multiply the modulus, but the angles in the exponential are added, which gives you ei theta plus theta 2, which rotates the outcome vector. Now, some relationships between sine and cosine that we should know, like sine theta, as you know, is equal to the opposite side of the angle divided by the hypotenuse, which is b, the height of z, divided by r, correct? Then b equal r sine theta. Cosine theta is equal to the adjacent side divided by r, so a divided by r. Then a is equal to r times cosine theta. R, the modulus, as you know, is equal to z within pipes or within the absolute value symbol is equal to square root of a squared plus b squared. And theta, of course, is equal to arctan, or tan to the power of -1 of b divided by a. Now, let's say z1 is equal to r1 ei theta 1, z2 is equal to r2 ei theta 2. Z1 divided by Z2 is equal to R1 divided by R2. We divide the modulus EI to the power of theta 1 minus theta 2, because these are powers. The angles are within the power of the exponential, so you subtract them. Okay? You subtract theta 2 from theta 1 instead of dividing like you did with the modulus. So Z1 divided by Z2 is equal to R1 divided by R2, which is normal or intuitive. EI, however, theta 1 minus theta 2. As for, so remember, for the division, we subtract for the exponents. As for the multiplication, we should add. It's logical. So Z1 times Z2 is equal to R1 times R2. For the modulus, it goes normally, okay? But for the angles, it gives us, so R1 times R2, EI, theta 1 plus theta 2. When you multiply exponents or numbers having powers, okay, you need to add the powers together. Like, it's like 2 to the power of 3 times 2 to the power of 1. It gives you 2 to the power of 4, which is 16. Okay, try it yourself. Now, the Moivre theorem gives us the following. So let's say you have a number z to the power of n. Okay, this becomes equal to r to the power of n times ei n theta, which also can be written r to the power of n rather, cosine n theta plus I sine n theta. Example, z equal 1 plus I. Okay, so what are we supposed to do with this? Let's try to convert it to cosine and sine form. I don't remember what was this example about. The modulus, okay, at first we need to get the modulus. Modulus of z is simply equal to square root of 1 square, correct? The real part square, which is a square, plus the imaginary part, which is not I. It is whatever is multiplied with I, which is 1. So 1 square plus 1 square is equal to square root of 2. That's the modulus value. Now, try to think about the argument of z, or the angle. So what would you think it would be? Argument of z is equal to 10 to the power minus 1 of b divided by a, which is 1 divided by 1, equal 1, which is what? 10 of theta. If it's equal to 1, then you have an angle, okay, that divides the 90 degrees of the axis, which is pi over 2 over 2, which is pi over 4, because in such case you have b and a both, because you know a is equal r cosine theta, b equal r, like the cosine and the sine would be equivalent and equal in such case to square root of 2 divided by 2. So the 10 theta gives us 1, okay? Theta in such case, or the angle, would be pi divided by 4. Exponential form, in order to write this form in the exponential form, you simply place square root 2, which is r, okay, right behind the exponential. So the form is rei theta. R is equal to square root 2 times e, I is always there, okay, within the exponential, times the argument of z, which is pi over 4. So square root 2 ei pi divided by 4. In the polar form, so to convert it to the polar form, which is cosine and sine, you write z is equal to square root of 2 times cosine pi divided by 4 plus e sine pi divided by 4. Remember, I is always multiplied by the sine, okay, not the cosine. Which gives you, by the way, if you solve it back, this gives you, okay, square root 2 divided by 2, square root 2 divided by 2, which gets you back to the value, the original value of z. Okay? Evaluating z squared, which is equal to z times z. Z squared, okay, is equal to 1 plus I times 1 plus I, or 1 plus I squared, which is equal to 1 plus 2I plus I squared, which is minus 1. 1 minus 1 is equal to 0, so we remain with 2I, which is a pure imaginary value. Okay, then z is equal to square root 2, okay, in such case, yeah, the new, z is equal to square root 2 to the power of 2, okay. Here we are evaluating actually z squared, not z. Then times ei, 2 pi divided by 4, so it's equal to square root 2 square is 2 times ei, 2 times pi divided by 4, so it is pi divided by 2, which is equal to 2 cosine pi over 2 plus ei sine pi over 2, or 2i. Again, the square value rotates, okay, it scales and rotates the vector, the complex number. How did it rotate it? Because you see 2i is on this y-axis, which has a 90-degree value, and it is double the length. Okay, exercise. Let z1 equal 1 plus I, z2 equal 1 plus 3i. Compute z1, z2, z1 divided by z2, and z1 to the power of z2. Okay, you can pause the video and try to go at it yourself at first before seeing the solution. So let's start with z1 times z2. z1, z2 is equal to 1 plus I times 1 plus 3i, which is equal to 1 plus 3i plus I minus 3, which is 3i squared. Okay, equal 1 plus 4i minus 3 equal minus 2 plus 4i. Minus 2 is the real part and plus 4 is the imaginary part. z1 divided by z2 equal to 1 plus I divided by 1 plus 3i. What should we do in such case? We simply multiply the denominator by its conjugate and also the numerator to get rid of the imaginary part and to keep the value the same. So what is the conjugate of 1 plus 3i? It is simply 1 minus 3i. So z1 divided by z2 is equal to 1 plus I times 1 minus 3i in the numerator and the denominator. Denominator is 1 plus 3i times 1 minus 3i equal 1 minus 3i plus I, okay, minus 3i squared, which is plus 3, equal 4 minus 2i divided by 10. Also, we can regroup it in this way, which is equal to 4 divided by 10 minus 2i divided by 10, or 2/5, 2 divided by 5 plus minus I over 5. Real part is 2 over 5 and imaginary part is minus 1 divided by 5. z1 to the power of z2. Now try to think about it, how we can solve this one. You can pause the video again, and for any exercise you can do the same. Pausing the video, try to solve it yourself, then go back and see the solution. So we're going to use the exponential form because it is much easier to deal with the exponential rather than the Cartesian form, so to speak. Okay, z1 at first is equal to z1 modulus, or modulus of z1, e to the power of I argument z1. Okay, so z1 is equal in modulus to square root of 1 square plus 1 square equal square root of 2, and argument of z, which is argument of z1 here, is equal to 10 to the power minus 1, or arg 10, 1 divided by 1, which is pi divided by 4. this is Z1 equal square root to EI pi 4. Now we need to raise it to the power of Z2. So now you can rearrange it. You can use the log. You see, Z1 is equal to exponential of log Z1. This is another way to rewrite it. So it is equal to log Z1 equal log R EI theta, correct? Equal log R plus log EI theta equal log R. You see, log EI theta is I theta. So we transitioned into the log of Z1, which is equal to log R plus E or I theta. Why? Because log AB is equal to log A plus log B, and log of the exponential of something gives us the angle, the something, correct? So log En or Ex or E alpha gives us back alpha. So log Z1 is equal to log square root of 2 plus the angle, which is I pi divided by 4. Okay, the angle times I, of course. Then Z1 to the power of Z2 is equal to E log Z1, correct, times Z2. So Z1 to the power of Z2 is equal to E log Z1, which is Z1, times Z2 is equal to E to the power of log square root of 2 plus I pi divided by 4 times Z2, which is 1 plus 3I. Okay, and it gives us back the result underneath, which is, let us check it. I need to move the camera a little bit. Log 2 divided by 2 minus 3 pi divided by 4. Okay, EI to the power of I, 3 log 2 divided by 2 plus pi over 4. Okay, it's a little bit heavy in the solution, but you can get there easily. Okay, just solve it intuitively to get to this solution. Let Z equal 1 plus I square root of 3 and compute Z to the power of 8. Put the answer in standard form, the final answer. Okay, you can pause the video, try to solve it. Remember the Euler formula as a hint, and let's move. So modulus of Z. At first, we're gonna need the modulus and the angle. Modulus Z is equal to square root of 1 square, which is the real part square, plus square root of 3 square, which is 3 by the way, is equal to square root of 4 equal 2. That's the modulus. Now, arg Z is equal to 10 minus 1 to the power of minus 1 square root divided by 1 equal 10 to the power of minus 1 square root, which gives us pi over 3. Remember, because 10 is equal to sine divided by cosine. Sine pi over 3 is square root of 3 divided by 2, correct? And the cosine of pi over 3, which is 60 degrees, gives us 1 over 2. The 2 factors out, so we are left with square root of 3, which is 10 minus 1 of square root of 3. What gives us this value of the tangent is pi over 3 radians. That's the angle, or again 60 degrees. Let's elevate it to the power of 8. Then Z to the power of 8 is equal to, again, the modulus to the power of 8 times the exponential of I, 8 pi over 3. Okay, so here we raise it to the power of 8, but for the angle we multiply by 8. Okay, as if adding the angle 8 times, which is equal to the power of 8 times cosine 8 pi over 3 plus I sine 8 pi over 3 equal to the power of 8 times cosine. Okay, now you see you have 8 pi over 3 is actually 6 pi over 3 plus 2 pi over 3, correct? 6 over 3 pi is 2 pi. It is a full cycle, you can cancel that out. Plus 2 pi over 3 plus I sine 2 pi plus 2 pi over 3. 2 pi is 2 pi n. It is a full rotation. You can remove it. So which is equal 2 to the power of 8. Now, 2 pi over 3 is simply pi minus pi over 3. So 2 to the power of 8 cosine pi minus pi over 3 plus I sine pi minus pi over 3. So what it gives us, you see, cosine pi minus alpha is minus cosine alpha. These are trigonometric identities, if you remember, okay? Plus I sine pi minus pi over 3, sine pi minus alpha is equal to sine alpha, okay? Because these are the two sides of the y-axis in the unit circle, okay? So the sine remains positive on both sides, but cosine, since it is the negative side for the x-axis, it becomes negative. So cosine pi minus alpha is equal to minus cosine alpha. Okay, what is cosine pi over 3? Which gives us 2 to the power of 8 minus 1 divided by 2, again as we mentioned, plus I square root 3 divided by 2 equal 2 or minus 2 to the power 7. Why? Because 2 to the power of 8 divided by 2. Okay, you deduct 1 from the power of 2 plus I 2 to the power of 7 square root of 3, which gives us 2 to the power of 7 is actually 128 multiplied by minus 1 plus I square root of 3. So we've taken 2 to the power of 7, which is 128, outside of the parentheses as a common factor for the entire answer. Before getting to this next exercise, I want to point to something, that the Argand diagram that you see here written is actually the geometric representation of a complex number. So whenever we represent a complex number z on the xy axis, which are in the C universe respectively the real and the imaginary axis, this is called the Argand diagram. So for the exercise, show that e to the power of z bar, or the conjugate of e to the power of z, is equal to e to the power of the conjugate of z, or e power z bar. Okay, you can pause the video and try to solve it yourself. As a hint, however, z is equal to x plus iy. You can take it like that. Why? Because z is a complex number. It has two unknown parts, which are respectively the real part and the imaginary part, x and y. So z is equal to x plus iy, z bar is equal to x minus iy. Then e to the power of z bar is equal to e to the power of x minus iy, equal, of course, when you have a sum within the exponential power, these summed values, you can multiply them together. So e to the power of x minus iy can be replaced by e to the power of x times e to the power of minus iy. Okay, you multiply the different components because you have an added power. So it is equal to e to the power of x, which is not a complex number, by the way, multiplied by cosine y minus I sine y. Because e to the power of minus iy is actually a complex number, equal e to the power of x cosine y minus e to the power of x I sine y. Let's find out what is the value of e to the power of z bar, the conjugate of e to the power of z, completely. It is equal to also e to the power of x plus iy, which is equal also to e to the power of x times e to the power of iy bar, equal ex times cosine y plus I sine y bar, equal e to the power of x cosine y minus e to the power of x I sine y, which is equal to e to the power of z bar. So we've proven that these two are equal to each other. Now, show that if z, modulus of z is equal to 1, then z to the power of minus 1 is equal to z bar. How to prove that? At first, z to the power of minus 1 is the reciprocal, okay, the reciprocity of z, which is equal to, or the inverse function of, not inverse, yeah, the inverse of z is equal to 1 divided by z, which is equal to 1 divided by x plus iy. Again, how do we get rid of the imaginary part in the denominator? We need to multiply by the conjugate, both the numerator and the denominator. So it is equal to x minus iy divided by x plus iy times x minus iy, which is the conjugate of the denominator, equal x minus iy divided by x squared minus I squared y squared, which is plus y squared. Now remember, in B, the condition is if modulus of z is equal to 1, then z to the power of minus 1 is equal to z bar. So this entire denominator is 1, hence becomes x minus I y, okay, which is z bar. So modulus of z is equal to square root of x squared plus y squared, okay, which is square root of 1, correct? Now, you raise it to the power of 2, but it is the same concept. So modulus of z equals square root of x squared plus y squared. Modulus of z squared becomes x squared plus y squared. If modulus of z is equal to 1, then modulus of z squared is also equal to 1. So this entire denominator becomes 1. Hence, z to the power of minus 1 is equal to the conjugate of z, which is x minus iy. Part C. Let x plus iy divided by x minus iy, which is z divided by z bar, by the way. Another way to write it is equal to a plus ib. Show that a squared plus b squared is equal to 1. Okay. For this one and for any other exercise, you can pause the video, try to solve it yourself, and get back. So, a squared plus b squared, by the way, is actually a plus ib modulus, but squared, okay? So, let's find the modulus, because if we want to find the modulus of x plus iy divided by x minus iy, we need to also place the second side of the equality with a modulus, okay? Let's say a is equal to b, then modulus of a is also equal to modulus of b, capital B, as an example. Modulus of x plus iy divided by x minus iy together, okay, is equal to actually the modulus of the numerator divided by the modulus of the denominator. So it is the same concept. Let's say you place the modulus for the entire fraction, it is actually equal to modulus of the numerator divided by the modulus of the denominator. Same thing. It is equal to modulus of a plus ib. Modulus of the numerator is equal to square root of x squared plus y squared divided by modulus of the denominator is also square root of x squared plus y squared. Is equal to square root of a squared plus b squared. Hence, square root of a squared plus b squared is equal to 1. So you elevate both sides to second order, or like to the power of 2. Rather, as a consequence, as a result, we get a squared plus b squared is equal to 1. Chapter 2, Functions of Complex Variable. Definition and examples. Complex functions are functions that depend on a complex number z, where z, the variable itself, is dependent upon real and imaginary values. R of z, or Re of z, if you want to use the initials, equal a, and I of z, or In of z, the imaginary part, is equal to b, for z equal a plus ib. let z be equal to x plus I y. Then f of z, which is a function of z, is equal to uxy plus vxy I, with real and imaginary parts. However, instead of being simple real values, u and v are real valued functions with variables x and y. So you have x and y on the real part, which is the horizontal plane, so to speak, and x and y changing on the vertical plane or vertical axis of I, okay, which is the vertical plane. So you will get a 3D-like image, a 3D plotting, 3D graph. Examples, you have common functions such as polynomial, fz equal z squared plus z plus 1. Fz is equal to e to the power of z equal to e to the power of x times cosine y plus I sine y. We've seen that before. F of z is equal to log z, which is the logarithm. You convert it to log r e I theta because z can be represented as r e I theta. Log ab is equal log a plus log b, which gives us log r. R is also the modulus, another definition for it. So modulus of z is r plus log e I theta. Now log of the exponential of a number or a value gives us that value. So log e I theta, which is also arg z, another name for it, gives us I arg z. Okay. Now f of z is equal to cosine z, or f of z is equal to sine z, which can be rewritten, by the way, as cosine z equal eiz plus e minus iz over 2. Sine z is equal to eiz minus e to the power of minus iz divided by 2i. Why is that? Where did it come from? It came from the Moivre theorem, okay, which is the writing or like the form of z equal r e I theta equal r times cosine theta plus I sine theta. As you factor it out, you get the values of sine and cosine in respect of r e I theta, okay, with r equal to 1 because we're talking about the unitary disk here. Okay, so if you write z equal r e I theta with r equal 1 and its conjugate, you can get from them cosine and sine in respect of the exponentials. Limits and continuity. Continuity of a z function. A function f of z is continuous at a point z0 only when limit of f of z when z tends to z0 is equal to f of z0. Okay, that's the definition of continuity. Mind you that z0 or any z is expressed also as x plus iy. So it is defined or it is dependent on two axes instead of one. The value of the function at z0, or which is f of z0, is equal to the limit of f when z approaches z0, okay, which is limit z when z goes limit f of z when z goes to z0 should be equal to f of z0 if the function f of z is continuous at z0. As an example, and before getting to it, I need to point to something important, is that the continuity in the complex universe is different than that in the real universe, for the real numbers. Why? Because for real numbers, you're only checking on one dimension. As we mentioned, the real number is expressed on 1D line. However, for complex numbers, you have a definition on both x and y. Okay, so they change independence of two axes, the real and the imaginary axis. That's why for complex numbers, the continuity or the concept and definition of continuity is somewhat extended, okay, somewhat more complex, no pun intended, than in the real universe for real numbers. So checking the continuity of the following function at z is equal to 0, the function is z bar square divided by modulus z square when or whenever z is different than z0, and this function is equal to 0 for z is equal to z0. We need to verify the continuity, which means f of 0 should be equal to the limit of f of z when z goes to 0, which is z0 also. Okay, expand the function. At first, we need to evaluate z bar square divided by modulus of z square, and we will see why. So z bar square, which is the conjugate of z square, is equal to x minus iy square divided by modulus of z square is simply x square plus y square is equal to x square minus 2i xy, we're developing the numerator, minus y square divided by x square plus y square. Here is the caveat. We need to evaluate the limit along the real axis, which means for z is equal to x, the imaginary part should be 0 when testing on the real axis, okay? Then we need to get the limit along the imaginary axis. Both limits should be the same, should be equal, and together should be equal to f of z0 so that the function would be continuous. Otherwise, it won't be continuous. This is what I meant by saying that in complex numbers, it is a little bit different, a little bit more intricate and complex, so to speak, than when testing for a real universe. Okay, so evaluating the limit, again, along the real axis, y should be 0. The imaginary part should be 0. So you replace y by 0, limit for z going to 0 of x squared divided by x squared, because any other part multiplied by y becomes 0, is equal to x squared divided by x squared, which is 1. Limit along the imaginary axis, so z would be equal to iy. Why? Because along the imaginary axis, the vertical axis, x is equal to 0. Imagine it in your mind, okay? Any value on the imaginary axis would have x equal to 0. So it gives us limit minus y squared divided by y squared, which is equal to minus 1. Okay, so we've gotten both limits on the real axis, the first one, and along the imaginary axis, the second. As you notice, they are different, and in both cases, they are not equal to 0. None of them is equal to 0. But this gives us an idea that the limit does not exist, and the function is not continuous for z equal 0. Okay, why? Because limit for x squared divided by x squared along the real axis when z goes to 0 is different than that of minus y squared divided by y squared on the imaginary axis. The limit does not exist, so f is discontinuous or is not continuous at z equal 0. Another notion here is that having the same value for the limit on both axes, the imaginary and the real, is called path independence, which is necessary for f of z to be continuous at that point. Path independence means that whether you're going on the x-axis, y-axis, or any other direction, by the way, here we have x and y alone, okay, these are the possible directions, they should lead to the same point. So no matter from which way you approach it, you approach the limit, you should get to the same point, to the same limit value, to f of 0. Now try to practice on this one. If you want, pause the video and come back to the solution. F of z is equal to x squared y divided by x squared plus y squared for z different than 0, and 0 for z equal to 0. This does not necessarily mean that the function is continuous at z equals 0. It might be like perforated, or there might be a puncture. This is what we mean. So let's check out. Does the limit exist at z tending to 0, or when z goes to 0? And checking the continuity at z equals 0, almost the same question, both of them. Okay, let's check the limit. At first, again, limit on the real axis, which is for z equal to x and y equal to 0. Okay, the imaginary part should be 0, is equal to limit of f of z, or limit of 0, because y is equal to 0. So it is 0 over divided by x squared equal to 0. Then the limit exists. That's the first thing for, of course, only the real axis. We've proven the limit exists on the real axis. Now, limit on the imaginary axis, y-axis, real part is 0. So x equals 0, the limit is 0 divided by y squared equal 0. Limit along the direction y equal x, which is the first bisectrous, by the way. You simply replace y by x within the equation, which gives us limit when z goes to 0. By the way, when z goes to 0, both x and y go to 0, which is the same thing. That's why we can write it like this. So limit z goes to 0 of x to the power of 3 divided by x squared plus x squared, which is 2x squared, equal to limit of x divided by 2, or 0 divided by 2, which is 0, because x3 divided by x squared gives us x. You can factor them out. Another direction, limit along the direction y equal x squared. So you replace y by x squared, which gives us limit when z goes to 0 of x to the power of 4 divided by x squared plus x to the power of 4. You factor out x squared in the denominator, so x squared times 1 plus x squared. You divide x4 by x squared. It gives us x squared divided by 1 plus x squared. So the limit is equal to 0 divided by 1. Okay? You replace x by 0. Then f of z is continuous. At first the limit exists, and f of z is continuous at z0, because for z is equal to 0, the function is equal to 0. It is given, okay, within the problem. More than that, we have proven path independency, which means the limit not only exists, but it has the same value from all the different directions. It is independent of the path. So no matter what direction you take, you end up with the same limit. It's kind of like a convergence, okay? The limit is 0 from wherever you go, or from whatever direction you follow, whether the x-axis, real axis, imaginary axis, or y equal x, the first bisectrous, or y equal x squared. Complex differentiability and derivative. The function f of z is differentiable at z within C, the complex universe, if the following limit exists. And the limit is taken from all different paths of the complex plane having the same value. So the limit is the following: limit of z going to z0 of f of z minus f of z0 divided by z minus z0, which might be familiar to you in the real numbers. because it is the same, almost the same concept of the tangent or the slope of a tangent against the complex function in this case. Cauchy-Riemann equations. These equations are necessary to demonstrate whether the complex function is differentiable or not. Okay, so let f of z be equal to uxy plus vxyi, where z is equal to x plus iy and u v both belong to real numbers. F is complex differentiable at z equal x0 plus iy0, which is z0, if and only if the partial derivatives ux, uy, derivative of y in respect of x in respect of y, and that of v in respect of x and y exist and are continuous near z0. So the Cauchy, that's the first condition. The second condition is that the Cauchy-Riemann equations hold at x0, y0. This is how you demonstrate it. The partial derivative of u in respect of x should be equal to that of v in respect of y. That's the first caveat. The second is partial derivative of u in respect of y should be equal to minus partial derivative of v in respect of x. Okay? And again, on a second note, or as a reinforcing of the first condition, the partial derivatives for u and v in respect of x and y should exist, and the function should be continuous at z is equal to z0. So these conditions should hold true for f of z to be differentiable. The partial derivative of u in respect of x should be equal to partial derivative of v in respect of y, and partial derivative of u in respect of y should be equal to minus partial derivative of v in respect of x. As a reminder, u is the real part, which is a real valued function, but it is in the real part of f of z. And v is in the imaginary part. It is the imaginary part. So f prime of x is equal to, for example, derivative of f in respect of x equal to partial u divided by partial x, that's the real part, or the derivative this time, plus partial v divided by partial x, the derivative of v in respect of x, times I. This is the imaginary part. Example, f of z is equal to z squared, and we know that z is equal to x plus iy. So what would be z squared? Z squared is equal to x plus iy squared equal to x squared plus 2iy plus I squared y squared, which is minus y squared, by the way. Why? Because I squared is simply equal to minus 1. So z squared, we split the real part on one side and the imaginary on the other, is equal to x squared minus y squared, that's the real part, or u, plus 2xy times I, that's v. Okay, so let's derive partial u divided by partial x, or the partial derivative of u in respect of x is equal to x. Partial v divided by partial y, or partial derivative of v in respect of y is equal to x, then partial u over partial x is equal to partial v divided by partial y. So we passed the first test for Cauchy-Riemann. Second test, partial u divided by partial y is equal to, this is u in respect of y equal minus 2y. Okay, partial v divided by partial x, which is derivative of v, imaginary part, in respect of x is equal to 2y. Then, as a result, you have partial u divided by partial y, or derivative of u in respect of y, is equal to minus derivative of v in respect of x, equal minus 2y. So it complies with the conditions. Hence, f of z is differentiable. exercise. Of course, you can pause this one, try to solve it, and get back to the solution. Check if the following function is differentiable, which is f of z is equal to z bar, or the conjugate value of z, which is simply equal to x minus I y. Let's check for differentiability. So at first, u is x and v is minus y. Respectively, the real value of z bar rather, is x, and the imaginary value is minus y, which are two real valued functions again. So partial derivative of u in respect of x is equal to 1. However, partial derivative of v in respect of y is equal to minus 1. So the first condition has not been met. Why? Because partial u divided by partial x is different than the partial v divided by partial y. Here you have 1, here you have minus 1. Let's, in all cases, check for the other condition. Other condition, partial u divided by partial y, or partial derivative of u in respect of y gives us 0. Partial derivative of v in respect of x gives us also 0. So partial u divided by partial y is actually equal to minus partial v divided by partial x. But although the second condition complies, the first does not. So f of z is not complex differentiable anywhere. The difference would be, by the way, if both of the conditions were met, it would be differentiable everywhere. Now, what does that mean? Cauchy-Riemann's equations ensure two things. At first, that the function f of z preserves angles and curves, which is also called conformal mapping. If you can imagine it as an object, a shape in 3D Max or any other like modeling software, okay, you can stretch it, you can rotate it. However, the shape remains the same. You're not like messing or altering the shape itself. You are either scaling or stretching and rotating, but the curvatures and the features, the physical features, the external features of the mapping of the shape remain the same. And on the other hand, f of z behaves like complex number multiplication. Okay, so this function remains the same, guards the same shape, okay, when rotating and scaling. Let f of z be equal to modulus of z squared. Check the differentiability. If so, meaning if it is differentiable, compute f prime of z, the derivative of f of z, okay? At first, you can pause the video, of course, try to solve it and get back to the solution. So for z equal to x plus iy, f of z, which is the modulus of z, is equal to x squared plus y squared. F of z is actually the modulus squared. Modulus alone is square root of x squared plus y squared. Since f of z is equal to modulus z squared, then you remove the square root and you end up with x squared plus y squared. To check the differentiability, at first we need to split f of z into real and imaginary real valued functions, okay? The real part is u equal x squared plus y squared, which is the entire function. Imaginary part does not exist, so v is equal to 0. Let's test using Cauchy-Riemann equations. So, partial derivative of u in respect of x is equal to x. Partial derivative of v in respect of y is equal to 0. Partial derivative of u in respect of y is 2y, and partial derivative of v in respect of x is equal to 0. Hence, partial derivative of u in respect of x is different than that in respect of v in respect of y, and partial derivative of u in respect of y is different than minus partial derivative of v in respect of x. So f of x is not differentiable everywhere, okay, is actually not differentiable anywhere except for one specific special case, which is when x and y are 0, which is the origin, by the way. So for x equals 0 and y equals 0, you get these conditions satisfied, which is partial u over x becomes equal to partial v over y, and partial u over y becomes equal to partial v over x. This is the only case where this condition is satisfied and where the function f of z is differentiable, which is at z equals 0 or z equal x plus iy, where x is equal to 0 and y is equal to 0. Let's compute f prime of z for this special case. What is f prime of z? How do we compute that? If you remember, it is limit when z goes to z0 of f of z minus f of z0 divided by z minus z0. The same equation of the slope of the tangent in real functions. This is actually the slope for the tangent in the complex realm, in the complex universe, for a complex function, which is 3D, you can say. Testing the differentiability at z equals z0, which is the special case. Z0 here is x plus iy, where x equals 0 and y equals 0. As we mentioned in the previous slide, this is the only point where f of z is differentiable. So let's evaluate f prime of z. It is equal to limit z going to z0, f of z minus f of z0, which is 0, divided by z minus z0, or z, because z0 is equal to 0. So it is equal to limit of modulus z square, which is f of z, minus f of z0, which is 0, divided by z minus 0, which is z, equal to limit, when z goes to 0, of z square modulus, if you remember, it is equal to z times z bar being the conjugate of z, divided by z. You eliminate z, so you get limit of z bar when z goes to 0, which is limit of x minus iy, the conjugate of z, when z goes to 0, which means when x goes to 0 and y goes to 0. But we need to test the limit for each case. Checking the limit on the real axis for x, for the real axis, y is equal to 0. The imaginary part would be equal to 0, which is this chunk here. So that gives us limit of x when x goes to 0 equals 0. Checking the limit on the imaginary axis, r of z equals 0 in this case, which means x equals 0, y different than 0. So it is the limit of minus iy when y goes to 0 equals 0. Hence the limit exists and is the same for both the real and imaginary axis. As a conclusion, f of z is differentiable at z equal 0. Analytic holomorphic functions. A function f is said to be holomorphic at a point z0 within C if it is complex differentiable at z0 and also the neighboring zone around it. A function is holomorphic basically on an open set U which belongs to C, which is a zone within C, within the entire domain of C. If it is complex differentiable, so it complies with the Cauchy-Riemann equations at every point of U. If you remember, we've mentioned before, it was differentiable everywhere. Here, it is not everywhere, but it should be differentiable within U, where U is a part of C. So it's not everywhere in C, it is everywhere in the zone U, which is a zone inside of C, inside the bigger C domain. A function is analytic automatically when it is holomorphic. Why? Because it should be, before it is differentiable, continuous, and it should have limits. And this leads to Cauchy's theorem, also power series and Taylor series, okay? Which We will see afterwards. A function f is analytic at a point z0 within C if it can be represented as a power series around that point. It can be developed into a power series. As an example, f of z is equal to, that would be the format, sigma n equals 0 to infinity, a of n, which are terms, times z minus z0 to the power of n, for z minus z0 are within the radius, okay? The radius of a circle, which is the domain, where the radius r is greater than 0. Shows that cosine z is analytic for all values of z. Compute its derivative and shows it equals minus sine z. And third, give the region where cotan z is analytic and compute its derivative. Okay, you can pause the video and try to solve it yourself. So let's get going. At first, z is equal to x plus I y. As you know already, cosine z can be expressed in terms of exponentials, which is equal to eiz, you need to memorize this formula, plus e minus iz divided by 2, which stems, by the way, from the Moivre theorem, which is equal to ei, we replace that by x plus iy, plus e minus I times x plus iy divided by 2, equal eix, e minus y, plus e minus ix, ey. And as you remember, ei something gives you cosine that thing plus I sine that thing, okay? So cosine z is equal to e minus y times cosine x plus I sine x, that's the first part, plus e y cosine x minus I sine x. So cosine z is equal to e minus y cosine x plus ey cosine x plus I, so we separated the real part and the imaginary part, plus I e minus y sine x minus e y sine x divided by 2. This is the imaginary part, which is vxy, by the way, and the first part is the real part, which is u. Okay, so we split the complex function into two parts, which are u and v, uxy and vxy, respectively, the real part and the imaginary part, with uxy is equal to e minus y cosine x plus ey cosine x divided by 2, and vxy is equal to e minus y sine x minus e y sine x divided by 2. Let's check the analyticity of the function using Cauchy-Riemann equations. So derivative of u in respect of x is equal to cosine x prime is minus sine x, correct? So minus e minus y sine x minus ey sine x divided by 2. We should remember that y is considered as a constant in such case, and partial derivative of v in respect of y is equal to minus e minus y sine x minus ey sine x, because y here is positive, divided by 2. Then partial derivative of u in respect of y is equal to minus e minus y cosine x plus ey cosine x divided by 2. Partial derivative of v in respect of x is equal to e minus y cosine x minus ey cosine x divided by 2. So as a conclusion, partial derivative of u in respect of x is equal to that of v in respect of y, and partial derivative in respect of y of u is equal to partial derivative of v in respect of x. Since these conditions are met, we conclude that f of z is analytic and differentiable throughout C. So f of z is equal to cosine z is differentiable with both derivatives existing and satisfying Cauchy-Riemann's equations. As a conclusion, it is analytic for all z. Compute its derivative and show that it equals minus sine z. Okay, so cosine z again is equal to eiz plus e minus iz divided by 2. We need to derive in respect of z this exponential dependent function. Okay, the second part, not the first part. So d cosine z divided by dz, or derivative of z cosine z in respect of z, is equal to I e iz minus I e minus iz divided by 2. You multiply the numerator and the denominator by I, so you get minus e iz, because you have I square here, then plus, because minus I square gives us plus 1, plus e minus iz divided by 2i, which is equal to minus e iz minus e minus iz, correct? So it is equal to minus sine z, because eiz minus e minus iz divided by 2i is sine z, and you have minus on the exterior of this fraction, which gives us minus sine z. Okay, notice how deducted the minus, or we moved it outside of the fraction. You simply multiply by minus on the inside and you remove the minus to the outside of the fraction. So you have eiz minus e minus iz times minus on the outside, of course divided by 2i, which is minus sine z. Polynomial and rational functions. A polynomial function f of z is of the form fz equal an z to the power of n plus an minus 1 z to the power n minus 1 plus 3 points plus a1 z plus a0, where a0, a1, a2 belong to the universe of C. They are complex in nature, and n is a natural number. It belongs to n, where n is the degree of the polynomial, the highest degree. Properties. Polynomials are differential and analytic everywhere in C. Fundamental theorem of algebra: every non-constant polynomial has at least one complex root. Roots: a degree n polynomial has exactly n roots. This includes the multiple roots when you have a square z, for example. Example: f of z is equal to z to the power of 3 plus iz squared plus 3z minus 1, where the degree here is simply equal to 3. That's the degree of f of z. Limits and continuity. Limit of a complex function f of z when z approaches z0 for z0 is within C exists when limit f of z if z goes to z0 is equal to L, a finite value. If for every epsilon greater than 0, okay, these are the conditions. So for every epsilon a very tiny infinitesimal number greater than 0, there exists delta greater than 0 such that when or whenever f of z minus L is less than epsilon, there exists, or actually z minus z0 is greater than 0 but less than delta. Okay, so for every epsilon number greater than 0, there exists delta greater than 0 such that fz minus L, the limit, is less than epsilon for z minus z0, an absolute value, is between 0 and delta. This is actually borrowed from the real definition of limits, except that for a complex number, z going to z0 can be approached from multiple directions. So the limit in all cases should be the same. It should be L from all different directions of approach when measuring that limit. Polynomial and rational functions. So, rational functions. A rational function is a two polynomials, one divided against another, of the form f of z is equal pz divided by q of z equal an zn plus an minus 1 zn minus 1 etc. plus a0 divided by bm z to the power of m plus bm minus 1 z to the power m minus 1 plus 3 points to b0 where q of x is different than 0. The roots of the numerator are called zeros. So the roots of the numerator are called zeros. Those of the denominator are called poles. These are the forbidden zones within the function. These are where the function cannot be defined. Okay? Actually, it blows up to infinity. We're going to see that. Rational functions are meromorphic, which means that they are holomorphic, defined throughout the domain, except some of the isolated areas, which are the poles. So these pole values within the denominator are forbidden values. It's like having an entire fabric, but it is punctured. Okay? So these punctured areas are areas where the function cannot be defined. Okay? So it is either punctured or it is stretched to infinity on those pole zones. The limit of a complex rational function behaves so similarly like the one for a real function. So if you have f of z is equal to p of z divided by q of z, then if the degree of p is less than the degree of q, so the denominator is larger, then the limit of f of z when z goes to infinity is equal to 0, because you are dividing by a much larger number. If degree of p is equal to degree of q, so both the numerator and the denominator have the same degree, then limit of f of z when z goes to infinity is equal to a constant coefficient. If degree of p, the numerator, is greater than degree of q, the denominator, then the limit of f of z when z goes to infinity is equal to infinity. Exponential functions, or e of z. So complex exponential function ez, for a complex number z is equal to x plus iy, e of z is equal to e to the power of x plus iy, or e to the power of x times eiy. We've already seen that. It would be just a reminder. According to Euler's formula, eiy is equal to cosine y plus I sine y. So e of z is equal to e to the power of x times cosine y plus I sine y. Properties of ez. So ez is complex differentiable, holomorphic, in other words, in all of C. It is differentiable throughout C. Differentiation, how to derive e of z in respect of z. So dez divided by dz is equal to ez. When we derive the exponential e to the power of z, it simply gives us ez. Addition, so ez1 times ez2 is equal to ez1 plus z2. Again, when we multiply two numbers, you add up the powers together. Okay? Periodicity, e of z is periodic in the imaginary direction. So you have e of z plus 2 pi I. Why? Because the real value, the real part, has no periodicity. It cannot be expressed as cosine and sine. Okay? It is e of x, but e I y gives us cosine theta plus I sine theta. So it has some periodicity. It has a cycle of 2 pi. So eiy is equal to eiy plus 2 pi, which is one cycle, equal cosine y plus I sine y. Modulus of ez is equal to modulus ex cosine y plus I sine y, which is equal to ex. Why? Because modulus of cosine y plus I sine y, ex is a constant anyway, is equal to cosinus square y plus sinus square y. So adding these two together, it gives us 1, which is the radius of the unit circle. Now the exponential function can be defined via its Taylor series, which is e to the power of z is equal to sigma, or sum, from n equals 0 to infinity of z to the power of n divided by n factorial. This is the Taylor expansion of ez, which comes in handy in many applications. This series converges absolutely and uniformly for all values of z. So for all values of z within C, this series arrives to a finite number. This is what converges means. Geometric interpretation: the exponential map sends horizontal lines on the constant x to circles of radius ex. Okay, this is how it works. And vertical lines map to spirals in the complex plane. So the vertical lines on the imaginary map to spirals in the complex plane, constant, so you have a constant y due to the vortex rotation of EI y. Okay, this is how geometrically it works. And again, as a reminder, imagine that any complex function is dependent on x and y, correct? But also x and y exist in both the real plane, which is the x-axis, and the imaginary or vertical axis, the imaginary plane, if you will, or the imaginary axis. So you have like a surface that changes in respect of the real axis on the horizontal line and the imaginary axis on the vertical line. Based on Euler's formula, you have cosine z. Again, as a refresher, because we've just seen these before. Cosine z is equal to eiz plus e minus iz divided by 2. Sine z is equal to eiz minus e minus iz divided by 2i. You have cosh z, or hyperbolic cosine, is equal to ez plus e minus z divided by 2, and sinh z, this is how they actually pronounce it, is equal to ez minus e to the power minus z divided by 2. This is the hyperbolic sign. Cosh square z minus sinh square z is equal to 1. Cot z, cotan of z, is equal to cosine z divided by sine z. Cosine square z plus sine square z is equal to 1. And secant z is equal to 1 divided by cosine z. So also you have tan z is equal to sine z divided by cosine z, and we can find it in respect of the exponentials, okay, their exponential values. So you can divide sin z, which is eiz minus e minus iz, divided by eiz plus e minus iz. You have the 2 is deducted, okay, it factors out. What remains, I think, is the I multiplied in the numerator, okay? And cosecant z, which is the inverse of the sine z. Logarithmic functions and branch cuts. Unlike in real analysis, the complex value of a logarithm is a multi-valued function defined by log of z is equal to log rei theta, if you remember, correct? Where, of course, log AB gives us log A plus log B, which is log R or modulus Z, that's the same thing, plus log of EI theta, theta being the argument of Z or the angle of Z. Log of the exponential of E or I arg Z gives us I arg Z, okay? So log EI theta simply gives us I theta, except instead of theta you have argument Z, which is the same thing. So modulus Z, Z here is the modulus of Z or length from the origin. Arg Z is the angle of Z. Arg Z can be expressed as arg Z equal theta plus 2 pi n, because if you go around the circle 1 full rotation, it doesn't change the value, which means that the angle is not unique and we can have infinite values that are multiples of different 2 pi i's. Okay. To define a single value, which is the principal value, we confine the argument in a limited interval, like arg z is between minus pi plus pi. This is also called the branch cut, okay? It can be defined in another term, which is a branch cut. So the branch cut for logarithm, we cut along the negative real axis or minus infinity to 0, for example. This prevents discontinuities and sudden angular shifts or jumps. Riemann surfaces. A Riemann surface is a geometric tool that allows us to adapt a multi-valued function into a single-valued function, which is also displayed in 3D, so to speak. It is by definition a one-dimensional connected complex manifold. The analogy is if you can imagine multiple sheets connected in a complex plane, that a multi-valued function located on the plane can be viewed as single-valued when observed on the surface. And these sheets, when connected together, form a 3D shape. Logically, for each point z, we are supposed to get one value, but a Riemann surface does a workaround to turn it into a single-valued function instead. Exercise. Let f of z be equal to the square root of z, the principal branch of the complex square root. Define the Riemann surface on which f of z becomes single-valued. This is important. So in other words, we need to define where f of z becomes equal to z. Second, describe the Riemann surface as branched covering of the complex plane. Third, determine the number of sheets and the location of branch points. You can pause the video and get back to the solution. Okay, so the first question, define the Riemann surface on which f of z becomes single-valued. Okay, the complex square root of z is multi-valued. It has two values for each non-zero z, correct? Corresponding to the two square roots of a complex number. Because square root of z, it means that z is either plus or minus, either negative or positive. To make square root of z single-valued, we define a Riemann surface R that consists of two copies or two sheets, one is positive and the other is negative, of the complex plane cut along a branch cut. A standard branch cut is the negative real axis, which is minus infinity to 0. We glue the two sheets in such a way that we transition from one sheet to the other when encircling the branch point at z equals 0, when turning around z equals 0. Second, the Riemann surface as branch covering of the complex plane. Okay, describe. So it is a two-sheet covering of the complex plane branched at z equal 0, for z equals 0 and z equal infinity, near any point other than the branch points. The covering is locally homeomorphic, so it is holomorphic, except for the disjoint, the point where there's no definition, okay, which is the disjoint union of the two disks. Near the branch point z equals 0, the sheets are connected such that going once around z equals 0 causes a transition from one sheet to the other. So on the first sheet, you have square root of z is equal to square root of r ei theta, or square root of r times ei theta divided by 2, because square root means to the power of 1 over 2. So within the angle, you multiply the angle, which is theta, which is argz, by the way, by 1/2. So theta is between minus pi to pi. That's the first sheet. The first half of, the first circle, so to speak. On the second sheet, square root of z is equal to square root r ei times theta plus 2 pi, meaning a full rotation. Okay, you see, you can have multiple copies. Each copy would be different of another 2 pi rotation around the same angle. So ei instead of theta, theta plus 2 pi divided by 2, which is minus square root of r ei theta over 2. Okay, that's the inverse direction. Third question, determine the number of sheets and the location of branch points. So there are 2 sheets in total, and the branch points are at z equals 0 and z equal infinity. This means that the Riemann surface is connected and the function square root of z becomes single valued on this surface. Conclusion: the Riemann surface for square root of z is a two-sheeted cover of the complex plane branched at z equals 0. That's the connection point, and z equals infinity. And it allows the multi-valued function square root of z to be treated as a single-valued analytic function on this surface. Another one, let f of z is equal or be equal to log z. First, prove that log z is a multi-valued function on C. Okay, you can pause the video, read the different questions, and try to solve them yourself. So we have second question, describe the construction of a Riemann surface on which log z becomes single valued. How, third question, is the surface related to the universal covering of C? And 4, what is the behavior of log z as you loop around the origin? So 1, log of z is equal to log REI theta, right? Because z can be written as REI theta. R is the modulus and theta is the argument. Equal log R plus log EI theta, which is equal to log R plus I theta. This function has infinite values in C. Why? Because for each angle equal theta plus 2 pi n, for each rotation you can have a different value. That's why you have infinite values in C. So log z can be rewritten as equal log R, which is a constant, plus I times theta plus 2 pi n, for n is a natural number. For n is within the range of 0 up to infinity. So you can have an infinite number of values. Second question, describe the construction of a Riemann surface on which log z becomes single valued. So Riemann surface when or where it becomes single valued is one branch cut around 1 to pi cycle, one rotation, correct? Each sheet or copy consists of one cut in 1 to pi, so we glue multiple sheets together to form a helix-like surface, so it becomes a spiral, okay, around the origin. Spiral going up, each sheet corresponds to theta within the range 2 pi n and 2 pi n plus 1, okay? So you have 2 pi n, one rotation, and 2 pi n plus 1, the second rotation. And you go to infinity with it. How is this surface related to the universal covering of C? The universal covering of C is referring to the mapping of log of z over C, which is the inverse function, by the way. Okay, we are talking about the inverse function. The same way it works for real analysis. When you have a function y equal fx equal to x squared, let's say, divided by x minus 1, and you need to find x in respect of y, which is the inverse of the function of y in respect of x. It works the same way for complex analysis. So again, the covering is simply the mapping through the inverse function of log of z. So w is equal to log z. You elevate both components, the left side and the right side, to the exponential. E w is equal to e log z, which is z. Then z is equal to ew. This is the mapping. Fourth question, what is the behavior of log z as you loop around the origin? Let's check it out. So f of z is equal log z looping around z equals 0 once each 2 pi I. Each loop is one sheet that makes a 3D curvature, which is a logarithmic curvature. As you connect the sheets together, one sheet constitutes one loop. It grows into an infinite spiral helix, as we mentioned already. Contours and contour integral. So a contour is a directed curve in the complex plane along which we perform integration, just like line integral somewhat. It can be a piecewise smooth path that can be composed of straight or curved segments and curved segments. parameterized by a function such as z of t, where t is between a and b, a finite interval, oriented having a direction from z of a to z of b. A circle centered at the origin with r radius. This is a closed simple contour, so a closed curve, so to speak, like gamma of t is equal to REIT, where t is between 0 and 2 pi, a full circle. Contour integration and Cauchy's theorem. Let's say f of z is analytic, holomorphic in other words, on and inside a closed contour gamma. Then integral of f of z dz gamma is equal to 0. Why? Because you are running into a full circle, so you're ending up at the same point where you started. In other words, you haven't gone anywhere, like an analogy or an intuition. That's why the integral around a closed curve should be 0. Cauchy's integral formula. Let's say f of z is analytic inside and on a simple closed contour gamma. A is a point inside of gamma. Then, in such case, f of a is equal to 1 divided by 2 pi I integral of f of z divided by z minus a dz. This allows the evaluation of an analytic function inside a region based on the boundary. Okay? So, in other words, you are evaluating the value of the function at a through this integration, which is 1 divided by 2 pi I integral over the contour of f of z divided by z minus a dz. If gamma is parameterized by z of t for t is between a and b, a closed limited interval, then integral over gamma of f of z dz is equal to integral from a to b f of z of t times z prime of t dt, where f is a function of z of t. Okay, we are getting f in respect of z of t, and z prime of t, of course, it is the derivative of z. It is the same formula for line integrals, but it has been imported for the complex analysis from the real analysis, but the same concept. Example, let f of z be equal to z square, where c is the circle of radius 2 traversed once clockwise. Clockwise meaning from 2 pi to 0, not the other way around. So z is equal to x plus iy, x is equal to 2 cosine theta. These are the polar coordinates, by the way. Y equal 2 sine theta. Or it can be rewritten in the exponential de Moivre formula format. So z is equal to 2 ei theta. Why? Because the radius is 2. And theta will be parameterized as t, where t is going from 2 pi to 0. So this is f of z is equal to z square, remember? So z square is equal to 2 ei theta square, or 4 times ei to t. Okay? Why? Because you elevate the modulus to the power of 2, but you multiply the power with the angle in the exponential. Remember that. This is z. Okay, so we need still z prime of t. Okay, so this is f of z, 4 ei to t. Z, of course, is equal to ei t, and z prime of t is equal to I eit. Hence, the integral is the following. Integral from 2 pi to 0 of f of z, z prime t dt, correct? Which is 4 times 2, 8, times I, ei 2t times eit. You add up the exponential powers, which means this is equal to ei 3t, correct? dt is equal to a divided by 3 e 3it from 0 to 2 pi, which is a divided by 3, 1 minus e 6 pi I, which is cosine 6 pi I, correct? Minus sine actually plus sine 6 pi I, which is a divided by 3, 1 minus cosine 6 pi plus I sine 6 pi. Sine 6 pi is just like sine 0, okay? Why? Because 6 pi is 6, actually 3 rotations around 0, but they get you back to 0, which gives you 1 minus 1 plus 0. Cosine 6 pi is 1. So 1 minus 1, 0, times 8 divided by 3, which is 0, okay? Which proves the equation. Why? Because when you have a closed circumference, a closed curve, the integral around that closed curve in the complex analysis should be 0, because f of z is holomorphic and all what we mentioned before. Exercise. Let f of z be equal to z bar, which is the conjugate of z, around the circle C counterclockwise with z modulus of z is equal to 1. Compute integral over C of f of z dz, which is the integral over the curvature or the circle C. Counterclockwise means it is the trigonometric direction from 0 to 2 pi. You can pause the video and try to do it yourself. Okay. So f of z is equal to z bar equal to 1 times e minus I theta. Why? Because as a proof, it is in the trigonometric form equal to cosine theta minus I sine theta. This is the conjugate of cosine theta plus I sine theta, which is e plus I theta, which is z. dz, which is the derivative of z, is equal to I ei theta, with z being ei theta, because the modulus or r is equal to 1. So integral from 0 to 2 pi of z bar dz is equal integral from 0 to 2 pi, z bar is e minus I theta, times ei theta times I, with theta being parametrized as t. Okay, remember that. Of course, here you have dt. I left that, okay, by accident. So it is equal to I, okay, e minus it times e it gives us 1, because you add up the powers, it gives you a power of 0, so e to the power of 0 is simply 1. The integral gives us, I is a constant, of course, so it is I times t between 2 pi and 0, which is 2 pi I. That's the final result. Now here we notice something, that the integral that was supposed to give us a result of 0 around the circle, because we are integrating in a closed loop, okay, where you start is where you finish. The integral should be 0. Since it is different than 0, then Cauchy-Riemann theorem does not apply, okay? In other words, f of z is equal to z bar is not analytic. That's why the integral can be different than 0. Because if you test for analyticity, f of z equal to z bar is not analytic. That's why you get an integral result around the circle of 2 pi I. Again, it is different than 0. Exercise. Let f of z be equal to 1 over z around the circle C, counterclockwise with modulus of z equal 2. Compute integral over C, the circle, of f of z dz. You can pause the video, try to solve it yourself, and come back to the solution. So, z is equal to rei theta. This is the form of z, which is equal to 2ei t. Why? Because the modulus r is equal to, and theta has been parametrized into t. Then dz is equal to I eit dt, which is the derivative of z in respect of t. Let's place them back into the integral. So integral from 0 to 2 pi, because it is the trigonometric direction, of 1 over z dz is equal to integral from 0 to pi of dz over z, which is 2i eit over 2eit. So you factor out eit and 2, it leaves us with integral from 0 to pi I dt. I is a constant, of course, so it is equal to I times t between 2 pi and 0 equal 2 pi I. As you notice, it is different than 0. Okay, now, this does not match Cauchy's theorem. Okay, forget about this left part here. This result does not match Cauchy's theorem integral, which has one pole, which makes sense. We have one pole here at z is equal to 0. This is a pole. Why? Because when z is equal to 0, the limit of f of z becomes infinity. The function f of z blows up to infinity at z is equal to 0. It's not defined nor analytic in C because of that pole, which explains why the integral did not give us a result of 0. It is different than 0 due to this very fact. Since we have a pole at z is equal to 0 where the function is undefined, that's why you don't get a result for Cauchy's integral around a circle, a closed circle, as 0. We've gotten a completely different result, which is 2 pi I. Okay, that's why the integral is non-zero. Hence, f of z is not analytic inside of C. On the left, we are checking for z equal to show you how it is different for z equal to, okay, on the boundaries of the circle. So limit, as a reminder of how to get whether the function is defined at a specific point. So limit when z goes to z0, which is 2, of z minus z0 times f of z divided by z minus z0 equal limit when z goes to 2 of z minus 2 times 1 divided by z, which is f of z, times z minus 2 or z minus z0. It is equal to limit when z goes to 2 of z minus 2 divided by z minus 2 times z, which is equal 1 over z for z equal to, or 1/2, equal f of 2. So this is an exception here. It is a point where the function is defined, which is z equal to. However, for z is equal to 0, there's a pole, a zone where the function is no longer defined. Okay, it goes to infinity, which renders the entire integral different than 0, as we mentioned before, and again, which makes f of z non-analytic inside of C. Analytic functions and power series. Here we're gonna address series in the complex plane. So a function f of z is analytic at z0 if it can be expressed as a convergent power series in a neighborhood of z0. It means that it has a limited finite value around z0. Okay, it can be expressed as a convergent power series that does not go to infinity. In fact, in complex analysis, if f of z is analytic in a disk, then it has a convergent power series in that disk. In the context of complex analysis, differentiability does not necessarily imply a convergent Taylor series. Okay, so the formula would be sigma n equals 0 to infinity, an, which is a term multiplied by z, times z minus z0 to the power of n. Okay, so an is equal to f to the power of n, or like n's derivative of f at z0 divided by n factorial. An belongs to C and z0 is the series center. A power series converges absolutely at z minus z0 less than r, where r is the radius of convergence. Radius of convergence means all the values for which the power series itself are convergent, okay, are finite. So these are all the values of z for which the series converges. What is r? The definition of r, it is equal to 1 divided by the limit when n goes to infinity of the 1nth root of an. Okay, so instead of the square root, it is the root at the nth degree of the an term. Okay, we're gonna see it more clearly in the practice. On the boundary at z minus z0 equal r, convergence must be tested case by case at the boundary. Now Laurent series, okay, these are Laurent series, okay, Maclaurent, allow us for negative powers of z minus z0. So you have sigma n from minus infinity to plus infinity, an times z minus z0 to the power of n, where an is equal to nth derivative of f at z0, which is the center of the series, divided by n factorial, used in donut-like or donut-like annular regions, where you have like an annular region between r, small r, lowercase r, and uppercase r, okay, between two boundaries, where z minus z0 is between lowercase r and capital R, and n is less than 0 is called the principal part. Now, to give you a clearer perspective on R, the radius of convergence is simply the inverse of the limit of an plus 1 divided by an, okay, when n goes to infinity. So it is 1 over L, where the limit is equal to, or is that of, an plus 1, so the n plus 1 term divided by the an term when n goes to infinity. This gives us an idea, I mean the limit itself, where the function is heading at n going to infinity, or at n when n goes to infinity. The radius of convergence would be the inverse of that limit. So let's say that f of z is analytic at and near a point z0 within C. Then the Taylor series of f of z, which is the generalized Laurent series, if you will, about z0 is given by f of z equal sigma n equals 0 to infinity, f to the power of n z0, which is the nth derivative of f at z0, the center of the series, divided by n factorial times z minus z0 to the power of n. This is how we develop Taylor series. Fn z0 is the nth derivative of f at z0, the center of the series, and an is equal to fn, the nth derivative of f, around z0 divided by n factorial. Okay, so converges at z minus z0 less than r, which is the radius of convergence. Here we're going to bring up the concept of singularities and Laurent series. We have three types of singularities, and we're going to talk about them afterwards. You have the removable singularity, which is called, like a principal part of that removable is 0. Okay, it is when you have a point where the function is not defined, however, the limit at that point is finite. We're going to see examples for that, like sine z divided by z. When z goes to 0, it goes to 1. So the limit is finite, however, it is undefined for z equals 0 because you are dividing two zeros together. Pole, and we've seen the pole before, it is when you divide by 0. This is the pole. It is not a finite value when testing the limit, so it is a point where the function blows up to infinity. Okay, this is the definition of a pole. It has many terms in principal part. Finally, the essential. What is an essential singularity? It is an infinitely, or it has infinitely many negative power terms. Let's go more in depth into singularities. So what are the types of isolated singularities, and what is an isolated singularity anyway? Let z0 be an isolated singularity of a function f of z. In other words, f is analytic in a disk, which is between 0 and r being the radius of convergence. Z minus z0 is between these two values, 0 and r, but not at z0. So f is analytic throughout this disk except at that point. We classify isolated singularities into three types based on Laurent series, which is fz is equal to sum minus infinity to plus infinity an z minus z0 to the power of n, where an is equal to fn, or n's derivative of f, around z0 divided by n factorial. You have the removable singularity. It has principal part of 0, like 1, or like sine z divided by z. Okay, it has a finite limit, by the way. That's why it is removable. Then you have a pole. It has finitely many terms in principal part. However, it blows up to infinity around the function blows up to infinity, goes to infinity around that pole, when it approaches that pole. And the essential. The essential, it has infinitely many negative power terms. Like within this, it goes to many negative power terms within the Laurent series. So that's why it's essential. It has a very chaotic behavior around, the function has a very chaotic behavior around an essential singularity. Okay? As for the removable singularity, for example, why is it is called removable? It's like a puncture within a surface. It can be removed and then the function becomes analytic. Okay? As for the pole, it goes to infinity at that point. You cannot remove it. And the essential, it has a chaotic behavior. Function has a chaotic behavior around that singularity, which is essential, because it has infinitely many negative power terms. Going back to the types of singularities, so the first one is removable singularity. An is equal to 0 for all negative terms. In other words, for the removable singularity, you have no negative powers in the Laurent series. Okay? You have no z to the power of minus n, so to speak. This is what he's talking about. Okay? You have no negative powers. So basically, it becomes as a Taylor series. The function can actually be extended analytically at z0 by defining the limit of f of z when z goes to z0 is equal to f of z0. As you remember, we mentioned that for the removable singularity, the limit exists and it is finite, although the point itself is not defined. Okay, the function is not analytic necessarily at that point. Second, pole. Definition. So there exists a positive integer m such that a of m or a minus m different than 0, a minus n equals 0 for all n greater than m. Okay, so you get to a point, in other words, to break it more simply, okay, z0 is called a pole of order m whenever at that pole f of z goes to infinity as z goes to infinity. Okay, so at that point you have a point, not necessarily like there's a z value where the function, the complex function, goes to infinity. It blows up, in other words. This is why it is called a pole. Especially when you're dividing by something, when you have a denominator, the roots of the denominator are actually poles. These are the values that make the denominator 0, which makes you divide by 0 and gets you infinite values. This is where the function blows up, at these poles. By the way, on the other hand, although we haven't addressed that yet, the residues are actually the roots within the numerator, but we'll get to that later. Essential singularities. Definition. It has infinitely many negative power terms, or they have many negative power terms infinitely in the Laurent series. No pole, not removable. Function exhibits wild behavior near the singularity. This is called Picard's theorem. So, near an essential singularity, f of z comes arbitrarily close to every complex number. In other words, it's all over the place, so to speak. Okay? So, the function exhibits a very complex, like a very intricate and weird behavior around that essential singularity. As an easier explanation, to break it more simply, a singularity is a point where a complex number misbehaves erratically and it's not differentiable, okay, because it's not defined, or the function rather is not defined at that point. One removable singularity is like a tiny hole or puncture on the road that you can remove or patch, and the complex function is fixed. Once it is removed, it becomes analytic, in other terms. Second, pole. The pole is where a complex function goes to infinity. It blows up like a high spike in the road. 3. Essential singularity. This is when the function is all over the place, highly chaotic in behavior at that point, and there's no limit or pattern for it. to give you an analogy, it's like you have water within a glass and you're stirring it in a chaotic, random manner. Like you're shaking the glass of water, so the water is almost all over the place. It's covering multiple areas, multiple values. Cauchy-Riemann theorem, okay, another theorem I wanted to introduce. Let f be holomorphic in a punctured neighborhood of z0. So it is analytic except at that point, i.e. z minus z0 is between 0 and delta, and suppose that z0 is an essential singularity of z. Then the image of z on every neighborhood of z0 is dense in C. Dense meaning it covers multiple values. Okay, this is the same reference for the essential singularity definition. If f has an essential singularity at z0, then for any neighborhood around z0, f of z takes arbitrarily almost every value in C. So the same way as saying it is all over the place. Identifying the type of singularity. Given a function f of z and a point z0, to get the singularity, you need to go by these steps. At first, simplify the function near z0, check limits or try series expansion, use Laurent series in annual region, series with E by the way, look at the order of the pole if it's a pole. If nothing cancels out or simplifies, you get strange behavior leading to essential singularity. Common Laurent series. These series should be memorized because they come in handy when solving for residues or poles or zeros. By the way, there's a distinction that should have been made before. Not the residue is the root of the numerator, but rather the zero. The roots of the numerator are called zeros, and you can find from them the residue. And those of the denominator are called poles. So, common Laurent series, e to the power of z is sigma n equals 0 to infinity of z to the power of n divided by n factorial. If you solve the first few terms, you get 1 plus z squared divided by 2 factorial, etc. Log 1 plus z is equal to sum from n equal 1 to infinity minus 1 to the power of n plus 1, z to the power of n divided by n equals z minus z squared divided by 2, etc. 1 divided by z minus 1, you can write them down by the way, is equal to sum n equals 0 to infinity of z to the power of n. And you have the sine and cosine. Sine z is equal to sum n equals 0 to infinity minus 1 to the power of n, z 2n plus 1 divided by 2n plus 1 factorial, and cosine z, which is a little bit similar without the shift of plus 1, sum from n equals 0 to infinity minus 1 to the power of n, z2n divided by 2n factorial, which makes sense because the cosine and sine are only different by a phase shift, which is the plus 1 here. Okay, it is translated into that addition within the n. Exercise. Identify the singularity at z equals 0 for the following function. F of z is equal to sine z divided by z. You can pause the video, try to solve it, and come back to the solution. So, what we have here is an undefined function at z equals 0, because you get sine 0 divided by 0, which is 0 over 0. It's undefinable, okay? However, the limit at z0 exists, which is the following. Limit f of z when z goes to 0 is equal to limit z going to 0 of sine z divided by z, which is the cardinal sign, which is equal to 1, okay? Because when z approaches 0, so does sine z approaches 0 in the same way, in the same quantity. So the division of both gives us 1. Which means that this is a removable singularity because the limit exists, it is a finite number, despite the fact that the function is not defined at z equals 0. Okay? Removable singularity means that if we remove value for z equals 0, the function would be analytic throughout the entire remainder of the domain. Okay, so we can make f of 0 equal 1 and fix the entire function. Now to go into more depths over how we found out that f of z around z is equal 0 has a removable singularity, we're going to develop f of z into Taylor series. Okay, so f of z, since the series is around z equals 0, Taylor series become just like Laurent series in such case. Okay, why? Because z0 is equal to 0. So f of z equals sigma from n equals 0 to infinity fn z0 divided by n factorial, that's the nth derivative of f, times z minus z0 to the power of n, is the same as writing it in a different way, because z0, remember, is equal to 0. So f of z is equal to sigma n equals 0 to infinity fn z0 over n factorial times z to the power of n, which develops, actually, if you remember Taylor series for sine z, it is given by z minus z3 divided by 3 factorial plus z5 divided by 5 factorial minus z7 divided by 7 factorial with an infinite number of alternations between minus and plus. Okay? Now the Taylor series development is given by z minus z3 divided by 3 factorial plus z5 divided by 5 factorial minus z7 divided by 7 factorial all the way to infinity. As a reminder, sine z as a formula for Taylor series is given by sigma, actually sum from n equals 0 to infinity minus 1 to the power of n times z to the power of 2n plus 1 divided by 2n plus 1 factorial. As a generic form for any series, the generic form is given by sigma n equals 0 to infinity an zn equal a0 z0 plus a1 z1 all the way to an zn. Hence, for sine z divided by z, the Taylor series become 1, because we are dividing by z, minus z squared divided by 3 factorial plus z4 divided by 5 factorial minus z6 divided by 7 factorial all the way. Noticing the pattern to establish the formula here, so the pattern becomes, or the Taylor series become, sigma n equals 0 to infinity minus 1 to the power of n times z to the power of 2n instead of 2n plus 1 because we are dividing by z over 2n plus 1 factorial. Now let's test the convergence. So the convergence test is given by the limit of an plus 1 divided by an when n tends to infinity. This should be equal to L, where L, the limit, is a finite value. An plus 1, of course, is the n plus 1 term of f of z, okay, of an. And an is this term. So it is the limit when n goes to infinity of minus 1 to the power of n plus 1. Instead of n, you place n plus 1. Divided by 2 multiplied by n plus 1 plus 1 factorial divided by minus 1 to the power of n divided by 2n plus 1 factorial is equal to limit when n goes to infinity of minus 1 to the power of n plus 1 divided by 2 times n plus 1 plus 1, all of them factorial, multiplied, you see we inverted the numerator and the denominator, multiplied by 2n plus 1 factorial divided by minus 1 to the power of n is equal to, this can be broken down because you see minus 1 to the power of n plus 1 is simply minus 1 times minus 1 to the power of n. 2n plus 1 factorial, and this also can be broken down if needed. Okay, and here you have 2n plus 3 factorial, on the other side minus 1 to the power of n. So these two can be factored out. Okay, so let's continue. Now, Remember that 5 factorial is given by 5 times 4 times 3 times 2 times 1 as an example. So 5 factorial can be rewritten as 5 multiplied by 4 factorial. N plus 1 factorial can be rewritten as n plus 1 times n minus 1, etc. all the way to 1, which is also n plus 1 times n factorial. So n plus 1 factorial is equal to n plus 1 times n factorial. 2n plus 3 factorial is equal to 2n plus 3, also as a conclusion, okay, following the same pattern. So 2n plus 3 factorial is given by 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So again, 2n plus 3 factorial can be broken down into the following 3 terms. It can be rewritten as 2n plus 3 multiplied by 2n plus 2 times 2n plus 1 factorial, which is what we want because we want to factor out 2n plus 1 factorial already existing in the numerator. So we get limit when n goes to infinity of minus 1 to the power of n times minus 1 divided by 2n plus 3 times 2n plus 2 times 2n plus 1 factorial multiplied by 2n plus 1 factorial divided by minus 1 to the power of n. We can factor out similar terms from the numerator and the denominator. So here goes minus 1 to the power of n. Also we can remove 2n plus 1 factorial. So you get minus 1 divided by 2n plus 3 multiplied by 2n plus 2, which gives us minus 1 divided by infinity equal 0. As a conclusion, the series converges. Now let's find the radius of convergence, in other words, the set of z values for which the series does converge. So the radius of convergence is given by r equal 1 divided by limit when n goes to infinity of the superior value of the square, actually not the square root, the nth root of an term. It can be actually rewritten as limit when n goes to infinity of an divided by an plus 1, which is the inverse of the limit value, equal to 1 divided by 0, which is equal to infinity. Then f of z is convergent for all real numbers, okay, for all values of z. Exercise: identify the singularity at z equals 0 for the following function: e to the power 1 divided by z. You can pause the video, try to solve it yourself first before getting back to the solution. So at first, the limit does not exist on z equals 0 because we are dividing by 0. So the function is not analytic. Let's check for the limits on the real axis and the imaginary axis. Limit along the real axis for z equal x because y would be 0. The imaginary part is given by limit f of z when z goes to 0 equal e infinity equal infinity. Limit along the imaginary axis, you have z is equal to iy in such case because x would be 0. This limit does not exist. Why? Because the function oscillates on a unit circle, okay, and z becomes equal to e minus I divided by y, which gives us cosine 1 over y minus I sine 1 over y. The Taylor series development for Ez is given by sum from n equals 0 to infinity z to the power of n divided by n factorial. So e of 1 over z has the series or the Taylor series form sum of n equals 0 to infinity z to the power of minus n. Why? Because instead of z you get, or you place 1 divided by z to the power of n in the denominator here. So it becomes z to the power of minus n divided by n factorial. So for the series of e to the power of 1 divided by z, we replace z by 1 over z, and the series becomes an infinite series with many negative terms. You can consider w is equal to 1 divided by z. So f of w is equal to e w equals sum from n equals 0 to infinity w to the power of n divided by n factorial, which becomes e to the power of 1 divided by z is equal to the sum n equals 0 to infinity 1 over z, which is w to the power of n divided by n factorial, equals z to the power of minus n divided by n factorial. So e to the power of 1 divided by z is given by 1 plus 1 divided by z plus 1 divided by 2 factorial z square plus 1 divided by 3 factorial z square, etc. Okay, so you get an infinite series with many negative numbers. The pole in such case is unremovable, okay? And the singularity is called an essential singularity. On another note, to explain why the terms are negative, it's not actually the terms, but rather the powers of the terms are negative. Okay, so the powers are negative because they are in the denominator. That's why you have an infinite number of negative powers within the denominator, because as you move them to the numerator, they are negative powers. That's why the series is called, or actually the singularity is called an essential singularity. It exhibits a weird behavior around z equal 0. Residue at a pole. The residue of a complex function at a pole is a key concept in complex analysis, particularly in evaluating complex integrals using the residue theorem. As a definition, what is a pole? The pole of a complex function f of z at z0 is a type of singularity where the function blows up or goes to infinity as z tends to z0. So a pole of order n means that the function behaves like 1 divided by z minus z0 to the power of n near z0. And by the way, in simpler terms, the residues, actually the pole or poles, are the roots of the denominator within a complex function. They are the roots of the denominator, so they are the values for which the denominator becomes 0. Definition of residue: the residue of f of z at a point z0 is the coefficient a minus 1 of 1 divided by z minus z0 in the Laurent series expansion around z0. So f of z is equal to plus a minus 2 divided by z minus z0 square plus a minus 1 divided by z minus z0 all the way, okay? All the terms that are within the denominator. Cauchy's residue theorem. So Cauchy's residue theorem is a fundamental result in complex analysis that provides a powerful way to evaluate contour integrals of meromorphic functions, which are functions that are analytic except for isolated poles, for zones that are poles within a domain where it is not analytic, it is not defined. Let f of z be analytic in a domain except for a finite number of isolated singularities such as z1, z2 to zn inside a positively oriented simple closed contour C, like a circle. Then I naught, or noded integral f of z dz is equal to 2 pi I sigma k equal 1 to m the residues of f zk. Okay, so it is equal to 2 pi I multiplied by the sum of all the residues for all the poles within this function. That is, the integral of f of z around C equals 2 pi I times the sum of residues of f at the singularities inside C. Steps to apply the residue theorem. First, we need to identify the singularities of f of z inside the contour C. Classify each singularity as removable, pole, simple or higher order, or essential singularity, and then compute the residue at each singularity. Actually, the residue applies only for poles, not for removable, not for essential. And then apply the theorem integral around a circle or a contour f of z dz is equal to 2 pi I times the sum of all residues. Real integral using residues. Residue theory allows us to evaluate certain real integrals using complex contour integration. This is used when it is difficult to evaluate with elementary variable techniques. If f of x is a real valued function on minus infinity plus infinity, we can extend it to a complex function f of z and consider a contour integral in the complex plane that includes the real line and a semi-circular arc in the upper or lower half plane. The forms that are usually evaluated using that method are improper integral over the real line, okay, like integral from minus infinity to plus infinity, p of x divided by q of x dx. Other types of integrals where we can use this type of method are integrals involving sine and cosine. By the way, pardon me for the typos, okay? So you have, as an example, integral from minus infinity to plus infinity cosine ax divided by x squared plus b squared dx, or integral from minus infinity to plus infinity x sine x divided by x squared plus 1 dx. The solving method, at first define a complex function f of z, choose a contour like from minus r to plus r for an arc of radius r, apply the residue theorem, integral f of z dz is equal to 2 pi I sigma residues in C, or the sum of residues in C, multiplied by 2 pi I. Show the arc integral CR f of z dz. When it goes to 0, r should go, or it needs to go to 0 when the radius goes to infinity, okay? And then conclude that the integral on the real axis is equal to the sum of residues times 2 pi I. That's the final conclusion. Residue calculation formula of order n. So let's say we need to get the residue, of course, of a pole. Residue of z equals z0, where z0 is the pole actually, is given by 1 divided by n minus 1 factorial, n is the order, multiplied by limit when z goes to z0 of the nth minus 1 derivative of z minus z0 to the power of n multiplied by f of z. Okay, when you see it in an exercise, it becomes clearer, okay? However, I would suggest that you would register this formula here because it will come in handy later, even if as a concept, okay, because you're gonna see an application for that. Example, evaluate the following integral from minus infinity to plus infinity of 1 divided by x squared plus 1 dx. As a reminder, the solving method is the following. At first, we need to define a complex function f of z in replacement of the x dependent function. Choose a contour C between minus r to plus r for an arc of radius r, for example. Apply the residue theorem, which is integral over a contour f of z dz is equal to pi I multiplied by the sum of all residues in C. Then show that the arc integral, for the arc integral f of z dz goes to 0 as r goes to infinity. And 5, which is the conclusion that the integral on the real axis is equal to the sum of residues times 2 pi I. Example, evaluate the following integral from minus infinity to plus infinity of 1 divided by x squared plus 1 dx. Of course, you can pause the video and then try to solve it yourself before we get into the solution. So, at first we need to define an f of z function. F of z is equal to 1 divided by z squared plus 1, which is a swapping between x and z. Okay, we swap or replace x by z, so you get f of z is equal to 1 divided by z squared plus 1. Poles are the roots of the denominator, or these are the values for which the denominator becomes 0. So let's evaluate the poles. To simply evaluate the poles, you place z squared plus 1 is equal to 0. So z squared is equal to minus 1 or I squared. Then z is equal to plus minus I. Only in this case, z equal plus I applies. It is within the circle contour because minus I is disqualified. To evaluate the residue of a pole, we simply need to get the limit for z going to I of z minus I or z minus z0, since it is a single root, so it is a root of order 1, given that minus I does not qualify as being a pole. So limit when z goes to I of z minus I multiplied by f of z, which is 1 divided by z squared plus 1, is equal to limit when z goes to I, z minus I divided by z minus I multiplied by z plus I, which is z squared plus 1, by the way. Okay, because I squared minus I squared gives us minus minus 1, which is plus 1. Equal limit when z goes to I of 1 divided by z plus I equal 1 divided by 2I. So let's apply the residue theorem. Now we've already gotten one residue, which is based on the poles that we have. Only one pole was qualified, which is z equal plus I. Z equal minus I is outside of the circle. So the only residue we've gotten is 1 divided by 2I. Hence, based on the residue theorem, you have integral f of z around the circle, dz, is equal to 2 pi I multiplied by the sum of residues, which is 2 pi I times 1 divided by 2I equal pi. Proving that integral of f of z dz around CR, which is the curvature, the circle, goes to 0 as r, the radius, goes to infinity. Let's consider at first the upper semicircle arc, which is for theta between 0 and pi, half a circle. Z is equal REI theta, the Euler's form for the complex number. Then dz is equal to REI theta d theta, and modulus z is equal to r. Okay, before we move on, I need to point that dz is equal to I REI theta. Okay, we needed to fix that error. So, absolute value of integral over gamma r, which is the upper semicircle between 0 and pi, of 1 divided by z squared plus 1 dz, is equal to integral from 0 to pi REI theta divided by z squared, which is REI theta squared plus 1 d theta. This becomes integral from 0 to pi REI theta divided by r squared EI2 theta plus 1, which we can solve by using a trick. We can factor out r and r squared plus 1 to the outside as constants, and what's on the inside becomes EI theta divided by EI2 theta. So it becomes integral from 0 to pi E minus I theta, because EI theta divided by EI2 theta is 1 divided by EI theta, which is E minus I theta. So this gives us, when we solve EI minus theta, because it is minus cosine, actually cosine theta minus I sine theta. So when we solve the integral, it gives us sine theta minus I cosine theta between pi and 0, of course multiplied by r divided by r squared plus 1, which is r divided by r squared plus 1 I plus I, okay, because sine pi and sine 0 gives us both ways zeros. So you are left with cosine pi, which is minus 1 times minus I, or plus I, minus minus I, because cosine 0 is 1. So 2I r divided by r squared plus 1, which goes to 0 when the limit of r, okay, when we are evaluating r going to infinity. So the limit for f of z dz, which is the limit of this quantity here, 2I r divided by r squared plus 1, which is 2I divided by r, is equal to 0. Another exercise for radius of convergence and convergence. So find the radius of convergence for the following series centered at z0 equal 2. The series is sigma or sum from n equal 1 to infinity of z minus 2 to the power of n divided by n squared. Of course, you can pause the video and try to solve it yourself first. So, sum from n equal 1 to infinity of z minus 2 to the power of n divided by n squared, which is equal to sum from n equal 1 to infinity. We are extracting here the an term of 1 divided by n squared, that's an, multiplied by z minus 2 to the power of n, that's zn. So an is equal to 1 divided by n squared. Let's get an plus 1. What is an plus 1? Because it will be needed to get the convergence limit of this series. An plus 1 is simply equal to 1 divided by, instead of n, you place n plus 1. So 1 over n plus 1 squared. So the convergence is given by the limit when n goes to infinity of an plus 1 divided by an in absolute value, equal limit when n goes to infinity, an plus 1 is 1 divided by n plus 1 squared, over or divided by 1 over n squared, which is equal to 1 over n plus 1 squared multiplied by n squared divided by 1, or n squared divided by n plus 1 squared, correct? Equal limit when n goes to infinity of n squared divided by n squared plus 2n plus 1. By the way, you can simply consider the highest order or highest powers to get the limit, okay? Here we are doing it in the classical way. So it is equal to limit when n goes to infinity of 1 divided by, here we have divided everything by n squared, from the numerator to the denominator. Or you multiply numerator and denominator by 1 over n squared. As simple as that. So 1 divided by 1, because n squared divided by n squared is 1, plus 2n divided by n squared, plus 1 divided by n squared. Here you have 2 divided by n, plus 1 divided by n squared. These zero out, so you are left with 1 divided by 1, which is 1. Radius of convergence. The radius of convergence, or in other words, all the values of z for which the series converges to 1, is given by r equal 1 divided by the limit when n goes to infinity of the nth root of an in absolute value, equal 1 divided by limit n goes to infinity of an to the power of 1 divided by n. The same thing but in a different formatting. Actually, this is the same as 1 divided by the limit of the convergence, so 1 over L. Or if you want, it is the limit when n goes to infinity of an divided by an plus 1. Okay, the inverse of the limit of convergence. It is given by 1 divided by the limit when n goes to infinity of 1 divided by n squared, which is an, to the power of 1 divided by n. When n goes to infinity, 1 over infinity goes to 0. So the power here of this number, whatever it is, becomes 0. Anything to the power of 0 is 1. So you get 1 divided by 1, which is 1. Hence, this series converges for z equal 1. Another exercise, find the radius of convergence for the following series. Sum from n equals 0 to infinity of minus 1 to the power of n factorial times z to the power of n divided by 2n factorial. Of course, you can pause this video, try to solve it, try to extract the an term, and then come back. Of course, we require the limit or the convergence of the series and the radius of that convergence. Sigma n equals 0 minus 1 to the power of n times n factorial divided by 2n factorial times z to the power of n. Here it should be obvious that z to the power of n is the z term and the an is what remains to the left, which is minus 1 to the power of n times n factorial divided by 2n factorial. Hence, an plus 1 is equal to minus 1 to the power of n plus 1 instead of n times n plus 1 factorial divided by 2 times n plus 1 all factorial. So the convergence is then equal limit when n goes to infinity an plus 1 divided by an equal limit when n goes to infinity of minus 1 to the power n plus 1 times n plus 1 factorial divided by 2 times n plus 1 factorial altogether divided by an, which is minus 1 to the power of n times n factorial times 2n factorial. So this becomes equal limit when n goes to infinity of minus 1 to the power n plus 1 times n plus 1 factorial divided by 2 times n plus 1 factorial multiplied by, we invert the denominator and the numerator to have a multiplication instead of division. 2n factorial divided by minus 1 to the power of n times n factorial. Now, as a reminder or review over how to work with the factorials and the powers, you have at first minus 1 to the power of n plus 1 is equivalent to minus 1 to the power of n times minus 1. Okay, because when you multiply them together, you add up the powers. 2n factorial is similar to 2 times n factorial. It is the same thing. n plus 1 factorial is equal to n plus 1 times n factorial. 2n plus 1 factorial, or 2 times n plus 1 factorial, equal to n plus 2 factorial, which can be broken down into 2n plus 2 multiplied by 2n plus 1 multiplied by 2n factorial. So let's develop and break down complex components of this fraction. Limit n goes to infinity of minus 1 to the power of n times minus 1 instead of minus 1 to the power n plus 1 multiplied by n plus 1 times n factorial, which is n plus 1 factorial formerly, multiplied by 2n factorial divided by 2n plus 2 multiplied by 2n plus 1 times 2n factorial, which was formerly 2n plus 2 factorial, multiplied by minus 1 to the power of n times n factorial. So we factor out from the numerator and the denominator the similar terms. You have minus 1 to the power of n both upstairs and downstairs, so to speak. You have 2n factorial and 2n factorial. You factor them both, and we are left with, actually you still have n factorial and n factorial in the denominator. The final resultant, or the final components that had survived this factoring, is minus 1 to the power of n plus 1 divided by 2n plus 2 times 2n plus 1. So the convergence is equal to the limit when n goes to infinity of minus n minus 1 divided by 4n squared plus 6n plus 2. You multiply by 1 over n the numerator and the denominator to find the limit. So we get limit when n goes to infinity minus 1 divided by n divided by 4n plus 6 plus 2 over n. So when n goes to infinity, you are left with minus 1 divided by 4n, because the other terms are either insignificant like 6 and or they become 0 like minus 1 over n and 2 over n. So limit n goes to infinity of minus 1 divided by 4n is equal to 0. The radius of convergence can be simply evaluated as the inverse of the limit of convergence, or r equal 1 divided by L, instead of going into the formula that we've seen before, which is 1 divided by limit n goes to infinity of the nth root of an, okay? Sub nth root of an, superior value. So the limit is, or we can also rewrite it this way: 1 divided by limit n going to infinity a n to the power of 1 divided by n equal 1 over L, or 1 over 0 equal infinity. In other words, this limit converges, or this series converges, for all values of z. Evaluate the following integral. Here we've gone back to what? Any hint here? These are the poles, the pole related exercises, poles and residues. Okay, so evaluate the integral for modulus of z equal 3, which is a circle of radius 3, of e to the power of z divided by z minus 1 squared multiplied by z plus 2. You can pause the video, try to solve it on a paper, and come back. It should have become easy at this point. At first, what are the different poles that we have? Okay, the poles again are the values of z for which the denominator becomes 0. The first pole, which is a simple pole starting from right to left, is z plus 2 is equal to 0. So z equal minus 2. This is a simple pole, meaning it doesn't have a power. Okay, so z equal minus 2 is our first pole, and for z equal minus 2, e to the power of z is defined and analytic. Okay, because it is equal to e to the power minus 2. So the numerator, in other words, does not become 0 in such case. Hence, what we get is the limit for z going to minus 2 of the function f of z is equal to e minus 2 divided by 0 equal infinity. So the function blows up at z equal minus 2, or goes to infinity in other words. Hence we have a pole of first order. Now for z equal minus 2 again, so the limit is equal to infinity, z equal minus 2, ez, for z equal minus 2, ez is defined and analytic. The function blows up at z equal minus 2, so it is a pole of first order. Let's check for z minus 1 square. For z minus 1 square, z equal to 1. This is the solution of the root. But it is a pole of the second order because it has the power of 2. Limit for z going to 1 of ez divided by z minus 1 squared multiplied by z plus 2 is equal to e to the power of 1, which is e. By the way, ez in such case is also defined and analytic. So the limit is equal to e divided by 0, which is infinity. The function as well here at z equal 1 blows up or goes to infinity. Then it's a pole, but it is of the second order. So z equal minus 2 an absolute value, and z equal 1. As you notice, they are both less than 3. So they are both inside the circle domain z modulus equals 3. As a reminder, the residue at a point, or a pole rather, z0 is given by 1 divided by n minus 1 factorial, where n is the order of the pole. So for example here z minus 1, the pole order is 2. For the second one it is 1. So residue at z0 is equal to 1 divided by n minus 1 factorial times limit, the limit should be outside, when z goes to z0 of the n's minus 1 derivative of the following: z minus z0 to the power of n multiplied by f of z. When you see it in practice, it will become much clearer within the exercises. By the way, we've used it before, but it was a little bit implicit because we didn't have a derivative. So we've gotten the limit of z minus z0 multiplied by f of z. Why? Because simply n was 1. So when you have n equal 1, this is insignificant here. The derivative of n minus 1 for n equal 1 is no derivative. It's simply the function itself, f of z, multiplied by z minus z0 without any derivation. And for 1 divided by 1 minus 1, which is 0 factorial, it is equal to simply 1. So integral of ez divided by z minus 1 square multiplied by z plus 2 is equal to 2 pi I, okay, that's the residue formula, sigma I equals 0 to n residues of z. So we're going to get the residues using this formula. Then using the second formula, we're going to evaluate the integral for gamma in z equal 3 in the circle of radius 3 for this entire function. The residue for z equal minus 2. Since it is a single pole, it is simply given by, and this by the way is the application for this formula. It is equal to limit when z goes to minus 2 of z minus z0, which is z minus minus 2, or z plus 2, multiplied by f of z, which is e to the power of z, divided by z minus 1 square times z plus 2. We factor out z plus 2, so it is equal to limit when z goes to minus 2 of e to the power of z divided by z minus 1 square, which is equal to e to the power of minus 2 divided by 9. This is the first residue for z plus 2. Evaluating the residue for z minus 1 square, which is z equal 1, a pole of order 2. We need here to apply the formula that we've seen previously, where the residue for z equal plus 1, it is equal to 1 divided by n minus 1 factorial, with n equal 2, so it is 1 factorial. Limit when z goes to plus 1, derivative to the order or degree of n minus 1, which is 2 minus 1, so the first degree derivative, over dz of z minus 1, or z minus z0, okay, to the power of 2, multiplied by f of z, is equal to limit when z goes to 1 of derivative over dz of e to the power of z divided by z plus 2, because z minus 1 square factors out. Okay, this is equal to u prime v minus u v prime divided by v square, where u is the numerator and v is the denominator. Prime is the derivative, so when we say u prime, it is the derivative of u, which is the numerator. So u prime ez times v, z plus 2, minus u v prime minus ez times the derivative of z plus 2, which is 1, divided by z plus 2 square. It is equal to limit when z goes to 1 of zez plus ez, because we developed the numerator, divided by z plus 2 square, which is equal, when z goes to 1, to 2e divided by 1 plus 2 square, which is 3 square or 9. So the residue for z equal plus 1 is equal to 2e divided by 9. So we've gotten the residues for z equal minus 2 and z equal plus 1, minus 2 and plus 1 being the respective poles within f of z. Hence, integral within the circle of modulus z equal 3 of ez divided by z minus 1 square times z plus 2 is equal to 2 pi I sigma I equals 0 to n of the residues, or the sum of the residues multiplied by 2 pi I. Let's evaluate the integral then. It is equal to 2 pi I sigma n equals 0 to, or I equals 0 to n rather, of the residues of z. So the sum of residues of z multiplied by 2 pi I, which gives us 2 pi I times 2e divided by 9, which is the residue for pole plus 1, plus e to the power of minus 2 divided by 9, equal to pi I divided by 9 multiplied by 2e plus e to the power of minus 2. Another one, evaluate the following integral, where the contour is the circle of modulus z equal to, or radius equal to, oriented counterclockwise, meaning in the trigonometric direction from 0 to 2 pi, of the following integral. So integral for z equal to ez divided over z squared times z minus 1 dz. You can pause the video, try to solve it before coming back as usual. Alright, so at first, this integral has 2 poles and 1 0. Okay, 2 poles, which is 1, a pole of order 2, z equals 0, and z equal 1. Okay, As a reminder, poles are the solutions or the roots for the denominator, and the zeros are the solutions or roots for the numerator. For the denominator, poles are z equals 0 and z equals 1. For the numerator, what we call zeros is actually 1, 0, e to the power of z equals 0. You elevate them, or you actually place ln before each one of them. ln ez equal ln 0, so z goes to minus infinity. So let's evaluate the integral for f of z when z is within the boundaries of a circle of radius 2, which is equal to pi I sigma n equal 0 to infinity, or I equals 0 to n, residues of z. For z equal 1, this is a simple order pole, so let's evaluate its residue. The residue for z equal 1 is equal to limit when z goes to 1 for z minus 1 multiplied by f of z, which is ez divided by z squared times z minus 1, which is equal to limit when z goes to 1 of ez divided by z squared, which is e to the power of 1, or e, which is of course Euler's number. Again, it's a simple order pole. We have another pole which is of the second order for z squared. So the residue for z equals 0 is equal to, or is given by this formula again. As a reminder, equal 1 divided by n minus 1 factorial for n equal 2 here, which is 1, limit when z goes to z0 or 0, derivative of n minus 1 order, which is 2 minus 1, so first order derivative of z minus z0 to the power of n, which is z minus 0 squared, times fz. So the residue for z equals 0 is given by limit when z goes to 0, first order derivative or first degree derivative of z squared multiplied by f of z, which is ez divided by z squared times z minus 1, equal limit when z goes to 0 of ez times z minus 1 minus ez divided by z minus 1 squared, which is equal to limit when z goes to 0 zez minus 2ez divided by z minus 1 squared, equal also, we factored out ez to the outside, times z minus 2 divided by z minus 1 squared. You replace z by 0, which gives us minus 2 divided by minus 1 squared, or minus 2. Let's evaluate integral f of z dz. So according to Cauchy's residue formula, integral for z equal to of f of z dz is equal to pi I sum of the residues within f of z. Remember now that the residues apply here, the residues that we found, given that the poles, both of them for z equals 0 and z equals 1, are within the domain of the circle. So the integral is equal to 2 pi I multiplied by the sum of residues, which are e and minus 2. Find the type of singularities within the following function. F of z is equal to z squared plus 1 divided by z minus 1 to the power of 3 times z plus 2 times e to the power 1 divided by z. As a reminder, the singularities are usually found in the denominator. Usually. Okay, as a hint, you can pause the video and try to solve it yourself first. Let's start with z minus 1 to the power of 3. So around z equal 1, z squared plus 1, which is the numerator, is equal to, hence z squared plus 1 is analytic. As for the limit of f of z for z goes to 1 is equal to divided by 0, which is equal to infinity. Hence f of z blows up or goes to infinity at z equal 1 with z minus 1 to the power of 3. So z equal 1 is a pole of third order. Now z plus 2. So at z equal minus 2, z squared plus 1 is also defined and analytic. As for the limit of f of z when z goes to minus 2 is given by minus 2 squared, which is 4 plus 1 equal 5, divided by 0 equal infinity. So f of z blows up to infinity at z equal minus 2. Hence, z equal minus 2 is a simple order pole, also non-removable pole, as the z equal 1, as z equal 1. Why first order? Because the power of z plus 2 is 1. That's why. For e to the power 1 divided by z. Okay. Now, when z is equal to 0, you have 1 over 0 within the power of the exponential, which is not defined or analytic. So we need to develop it into a series. By the way, in such case, the numerator is still analytic. Actually, it's a constant. So e to the power of 1 divided by z is sigma n equals 0 to infinity, z to the power of minus n divided by n factorial, which is 1 plus 1 over z plus 1 over 2z squared, etc. 1 over z, the power of the exponential, in such case, makes the exponential, which is e1 divided by z, have many negative arguments. Okay, so e to the power of 1 divided by z in such case will have many negative powers. And it exhibits a chaotic behavior at z equals 0. Thus, z equals 0 is an essential singularity. It's not a pole, so it cannot be counted within the residues. Let's get the residues of the poles. We will start with z plus 2, for which z equal minus 2 is the pole, or the value that renders the denominator 0. So the residue for z equal minus 2 of the function is equal to the limit when z goes to minus 2 of z minus z0, which is z minus minus 2 or z plus 2, multiplied by f of z, equal to the limit when z goes to minus 2 of z squared plus 1 divided by z minus 1 to the power of 3 multiplied by e to the power 1 divided by z, because z plus 2 factors out. Equal, we replace z by minus 2, so it gives us minus 2 squared plus 1, which is 5 in the numerator, and minus 2 minus 1 to the power of 3, which is minus 27, and e to the power of 1 divided by minus 2, which is e to the power of 1 half, multiplied by minus 5 divided by 27. Let f of z equal e to the power of z divided by z minus I squared. First, identify and classify all singularities of f of z. Then compute the residue of f of z at each singularity. Looking at the denominator, for z equal I, e to the power of I is analytic. The denominator tends to 0. Okay, so limit of f of z is equal to the limit when z goes to I of e to the power of I divided by 0, which is infinity. The function f of z blows up to infinity at z equal I. So z equal I is a pole of order 2 because it is squared. So the residue of the function for z equal I is equal to the limit when z goes to I of the derivative of z minus I squared multiplied by f of z, which gives us the derivative of ez, which is of course ez when z goes to I equal e to the power of I. Let f of z is equal z squared divided by z minus 1 squared multiplied by z plus 2. Identify and classify all singularities of f of z. Compute the residue of f of z at the singularity, and then evaluate integral of f of z for z modulus equals 3 within the circle of radius 3 of f of z dz. Let's start with z minus 1 squared. At z equal 1, z squared, which is the numerator, is defined and analytic. However, the limit for z going to 1 of f of z is equal to z squared divided by z minus 1 squared times z plus 2 when z goes to 1 equal 1 divided by 0, because this 1 becomes 0, z minus 1, which is equal to 1 divided by 0 equal infinity. So the function blows up to infinity at z equal 1, hence z equal 1 is an order 2 pole. For z plus 2, at z equal minus 2, the numerator z squared is defined and analytic as well. However, the limit of f of z when z goes to minus 2 is equal to 4 divided by 0, which is equal to infinity. So f of z blows up to infinity at z equal minus 2. Hence, z equal minus 2 is a simple order pole. Let's compute the residue of f of z at each singularity. Mind you that both of the poles are still within the circle z equal 3. That's for later. So, for z equal 1, we have a pole of the second order. Hence, the residue for z equal 1 is given by 1 divided by 1 factorial limit when z goes to 1 of the first derivative of z minus 1 square multiplied by f of z equal limit of the derivative of z squared divided by z plus 2. This is due to the fact that z minus 1 square cancels out. And this is the formula of the residues, as you remember. It is 1 divided by n minus 1 factorial limit of the n's minus 1 derivative of z minus z0 to the power of n multiplied by f of z. So, it gives us the limit when z goes to 1 for the derivative of z squared divided by z plus 2, which is equal limit of u prime v minus u v prime divided by v squared. So, u prime v is the derivative of the numerator, which is 2z times z plus 2, minus u v prime minus z squared times derivative of the denominator, which is 1, divided by z plus 2 square, which is denominator square, equal z square plus 4z divided by z plus 2 square. The limit for that at z equal 1 is equal to 5 divided by 9. Now for z plus 2, the pole is z equal minus 2. Let's find its residue. It is equal to the limit when z goes to minus 2 of z minus z0, which is z minus minus 2 or z plus 2 multiplied by f of z. Z plus 2 cancels out, which gives us the limit when z goes to minus 2 of z squared divided by z minus 1 squared, which is equal to z squared divided by z minus 1 squared for z equal minus 2 equal 4 divided by 9. Let's evaluate the integral of f of z dz for z modulus equal to 3 within the circle of radius 3. At first, z equal 1 and z equal minus 2 in absolute value are both within the circle of radius 3, so both of their residues can be counted. Hence, the integral of f of z dz, or z squared divided by z minus 1 squared times z plus 2 dz, is equal to pi I times the sum of all residues, which is equal to pi I times 5 divided by 9 plus 4 divided by 9, equal to pi I. Chapter 7, Conformal Mappings and Applications, Definition and Examples. Conformal mapping is a function that preserves angles locally. So a function f, defined on a disk where the disk is a part of C, is conformal at a point if it is analytic or complex differentiable and its derivative is non-zero at that point. So conformal maps preserve shapes of small figures. Key property, they preserve the angles between curves, including orientation. So other properties like the preservation of angles and local shapes, map harmonic functions to harmonic functions. We're going to check what harmonic functions are, like sine, for example, is a harmonic function in general. Simplifies geometry in complex domains, transform Laplace equation into itself, typically invertible and bijective on the domain of interest, but not necessarily globally. Okay, to give you a picture over what this definition means, if you can imagine a 3D modeling software. So the shape can be rotated, it can be stretched when you are modeling like a wall or a 3D shape. The shape itself does not change. It can be scaled up or down in size, it can be rotated, moved. However, the properties of the shape remain intact. They never change. And by the way, Invertible means that the mapping from one plane to another or one dimension to another can be reversed. Okay, you can reverse the mapping, like an inverse function, for example, f minus 1 of x, okay, is invertible because you can go back and forth from y equal fx and then from x equal f minus 1 of y, okay, back and forth. That's one. As for the bijectivity, it means that each element maps one-to-one from one dimension to another. Schwarz-Christoffel transformation, a special conformal map that maps the upper half plane to a polygon with internal angles alpha k pi at vertices zk. It is used to solve boundary problems with polygon regions. It is given by f of z equal a integral of pi from k equal 1 to n. Pi is the multiple product. Just like sigma is the sum, here is the product of multiple elements, which are t minus zk to the power of alpha k minus 1 dt plus b. Mobius transformations. A Mobius transformation, also called linear fractional transformation, is a function of the form f of z equal az plus b divided by cz plus d. A, b, c, and d are within the complex universe, and ad minus bc should be different than 0, which is, by the way, the determinant of the matrix a, b, c, d. If you notice, this is ad minus bc, okay? ad minus bc. Properties, the domain is the Riemann sphere, which is C union infinity. It is conformal wherever the derivative is defined. It maps circles and lines in the complex plane to circles and lines. Preserves cross ratios, a fundamental geometric invariant. It is bijective, so for each input you have an output, and invertible, meaning that you can go from a function to its transform and vice versa, which maps to another Mobius transform. Let's explore some of the Mobius transformations properties. So two transformations, f of z is equal to az plus b divided by cz plus d, and gz equal a prime z plus b prime divided by c prime z plus d prime. These two are equivalent if their coefficients differ by a scalar multiple. In other words, one is either larger or smaller than the other. Examples of geometric behavior based on some Mobius forms. Let's start with f of z is equal to az. Now remember, z can be expressed as x plus iy. Here you are multiplying both x and y with a. So not only the modulus will be changing, but also the angle, which is 10 to the power of minus 1 of y divided by x. So az induces scaling and rotation to the function. Then f of z is equal to 1 divided by z. This causes an inversion that reflects across the unit circle. F of z equals z plus b. It causes a translation. Why? Because actually the function is being displaced by a certain amount. It's like moving an object within a 3D software, by the way. And finally, f of z is equal to az plus b divided by cz plus d, which produces a compounded effect of all the upper behaviors that we've already seen. Mapping infinity and poles. If c is different than 0, then f of minus d divided by c, which means if we replace z by minus d divided by c, it gives us infinity. And f of infinity is equal to a divided by c. Now we will see these concepts clearer within the examples and exercises. Okay, I agree with that. If c is equal to 0, then f of infinity is equal to infinity. Okay? And f of z is equal to 1 divided by d times az plus b. Why? Because c is equal to 0, so you have d, a common denominator for az plus b. You can place it outside, so it gives you 1 divided by d times az plus b. As for the first one, if c different than 0, f minus d divided by c equal to infinity. So you replace z with minus d divided by c, which gives you infinity, and f of infinity equal a divided by c. Okay? Why? Because for z going to infinity, the limit is equal to a divided by c. That's why. Again, they will get, or they will become clearer within the exercises and the example. They are somewhat confusing over here. Inverse of a Mobius map. So let's say f of z is equal to az plus b divided by cz plus d. F minus 1 of z, which is the inverse, is given by minus dw plus b divided by cw minus a. You don't have to memorize that. Actually, there's a method where instead of f of z, you place w, and then you get z, the value of z in respect of w. Okay? So this is how you invert it. So instead of f minus 1 to the power of z, you can imagine this is z equal minus dw plus b divided by cw minus a. We will see how we can actually do that. Mobius transformation via 3 points or 3 points mapping. So when we have 3 points and their respective values, like f of the first point is equal to a specific value of the second point having second value, etc. So z1 w1, z2 w2, z3 w3. F will satisfy the following, which is f of z minus w1 times w2 minus w3 divided by f of z minus w3 times w2 minus w1 equals z minus z1 times z2 minus z3 divided by z minus z3 times z2 minus z1. I know it's a mouthful. Usually this is rarely used. Okay, we will find out the inverse Mobius transform through a much easier method that is based on inverting and finding the limits, etc. We will see that. We will check it. Hopefully, in this example, things become clearer. Again, the Mobius transform or transformation maps circles and lines to circles and lines in the complex plane. So find the Mobius transformation that maps the 3 points z1 equal 1 to w1 equals 0, z2 equal I to w2 equal 1, and z3 equal minus 1 to w2 equal infinity. You can pause the video, try to figure out the solution before we get into it ourselves. So f of z, the Mobius transformation, is given by az plus b divided by cz plus d. That's the standard form. So for z equal 1, f of z or w1 is equal to 0. Hence, a plus b divided by c plus d is equal to 0. You replace z by 1 and f of z by 0. So a plus b equals 0 and a equal minus b. F of z2 equal I is equal to 1. Hence, ai plus b divided by ci plus d is equal to 1. So ai plus b equal ci plus d. F of z3 equal minus 1 is equal to infinity. When do we get f of z equal to infinity? Or in other words, when does f of z blows up? It is simply when the denominator is equal to 0. So for z equal minus 1, d minus c is equal to 0. Why? Because for d minus c equal to 0, or the denominator being 0, with z equal minus 1, f of z goes to infinity. So as a result, d is equal to c. Given the relationships that we've obtained, we can deduce the following conclusion, which is b is equal to minus a equal minus c multiplied by I plus 1 divided by I minus 1, or a equals c times I plus 1 divided by I minus 1. In other words, we need to replace a, b, and c and d by a common factor that is one of them. So either a, b, c in respect of d, or a, b, d in respect of c, etc. F of z becomes cz multiplied by I plus 1 divided by I minus 1 minus C times I plus 1 divided by I minus 1 divided by CZ plus C, which gives you Z times I plus 1 minus I plus 1 divided by Z plus 1 times I minus 1 equal I plus 1 times Z minus 1 divided by I minus 1 times Z plus 1. Okay, you develop and you reduce, so we get 2i divided by minus 2 multiplied by Z minus 1 over Z plus 1, okay, after you factor out everything here, which is equal to minus I multiplied by Z minus 1 divided by Z plus 1. Find the Mobius transformation that maps the 3 points f0 equal I, f1 equals 0, and f infinity equal 1. As a reminder, a Mobius transformation has the following format. F of z is equal to az plus b divided by cz plus d. You can pause the video and try to solve it before we begin the solution. So let's place the different points. For z1 equals 0, f of 0 is equal to I, which is w1. For z2 equal 1, w2 equals 0. And for z3 equal to infinity, w3 is equal to 1. So for z1 equals 0, w1 equal I. Z equals 0 means you have b divided by d is equal to I, or b equal I times d. 2. For z2 equal 1, w2 equals 0, so a plus b divided by c plus d is equal to 0. Hence, a plus b equals 0, or a equal minus b. As for the third point, when z3 goes to infinity, w3 goes to 1, or f of z goes to 1. Okay, the question is, when does it actually go to infinity? Okay, or what happens when z3 goes to infinity? It is the limit of f of z when z goes to infinity, which is equal to a divided by c. So limit f of z when z goes to infinity equal a divided by c, because z becomes very large in respect of b and d. Hence, a divided by c is equal to 1, or a equal c. The next step is to find a common factor. So we've already gotten a equals c, a equal minus b, and b equal id. Okay, so since a equal minus b, then a equal minus id, because b equal id. A equals c, hence you can get c equal a, which is minus b, which is minus id. Okay, you see the relationship? So you place them back within the Mobius transform equation, and we get f of z is equal to minus idz, which is a formerly, multiplied by z, plus b, which is id, divided by cz plus d, with c equal minus id. You can factor out d by dividing the entire Mobius equation with d, and multiply the numerator and the denominator by I to get rid of the imaginary value within the numerator and a part of the denominator. So we get finally f of z is equal to z minus 1 divided by z plus I. Find the Mobius transformation that maps the 3 points f minus 2 equals 0, f0 equal minus 1, and f1 equal infinity. You can pause the video, try to solve it, and come back. Again, a Mobius transform has the following form, which is f of z is equal to az plus b divided by cz plus d. What are the different points? For z1 equal minus 2, w1 equals 0. z2 equals 0, w2 equal minus 1. Okay, and for z3 equal 1, w3 equal infinity. So, for the first part, f minus 2 equals 0, which gives us minus 2a plus b is equal to 0. The denominator cancels out because it is multiplied in the extremes by 0. Hence, b equal to a. For z2 equals 0, w2 equal minus 1. So b divided by d is equal to minus 1, or b equal minus d. For z3 equal 1, w3 equal infinity. When does the function go to infinity? It is simply when the denominator becomes 0. So f of 1 equal infinity, then cz plus d for z equal 1 is equal to 0, or c equal minus d. We have b equal to a, d equal minus 2a, and c equal to a. So we replaced everything by its equivalent in respect of a, okay, as a being the common coefficient or the common factor. You place it back within the equation, the standard form of the Mobius. It gives us az plus 2a divided by 2az minus 2a equal z plus 2 divided by 2 times z minus 1. So f of z is equal to z plus 2 divided by 2 times z minus 1, and notice that we got rid of a by dividing the entire equation with a. Now a heavier exercise. Let t of z be equal to z minus I divided by z plus I. First, show that t maps the upper half plane onto the unit circle d, with w is within c, and the radius, which is the modulus w, is less than 1. Then find the image of z equal I and z equals 0 under t. Finally, show that tz equal 1 when the imaginary part of z is equal to 0. At first, how to show that t maps the upper half plane onto the unit circle of radius less than 1. At the beginning, we need to replace z by its standard value, which is x plus iy, having real and imaginary values, of course. So t of z is equal to x plus iy minus I, which is x plus I as a common factor multiplied by I minus 1, divided by z plus I, which is x plus iy plus I, equal x plus I multiplied by y plus 1. Modulus of z is then equal to the modulus of the numerator divided by the modulus of the denominator, which is square root of x squared plus y minus 1 squared divided by square root of x squared plus y plus 1 squared. Since the numerator is less than the denominator, why? Because you have minus here. You have this minus 1 value. Then, as a consequence, as a result or a conclusion, modulus of z is less than 1. So it belongs to this upper plane unit disk. Second question, find the image of z equal I and z equals 0 under t. You simply need to replace z by I and 0 respectively. So, image of z equal I is given by t of I equal I minus I divided by I plus I, or 0 divided by 2i equals 0. Image of z equals 0 is minus I divided by plus I, which is minus 1. Third question, show that modulus of z is equal to 1 when the imaginary part of z is equal to 0. If the imaginary part of z is equal to 0, then y is equal to 0 within z equal x plus iy, as simple as that. So we know that z is equal to x plus iy if imaginary part of z is equal to 0, then z equal x. Hence, t of z is equal to x minus I divided by x plus I. So the modulus of t of z is equal to modulus of x minus I divided by the modulus of x plus I, which gives us square root of x squared plus 1 divided by x squared plus 1, which is equal to 1. Ez is equal to z minus I divided by z plus I shows that f is a valid Mobius transform. Find the image under f of the real line. R is within C, but the real, not the imaginary line. Okay, so there's a hint here. And finally, find the inverse transform. Let's start with A. So how can we prove that f, or t of z rather, is a Mobius transformation? A standard Mobius transformation has the following form. F of z is equal to az plus b divided by cz plus d, with ad minus bc should be different than 0. So let's identify a, b, c, and d. A is equal to 1, which is the argument multiplied by z in the numerator, b equal minus I, c equal 1, and d equal plus I. AD minus BC should be different than 0. Or in other words, you can rewrite it in the form of a matrix and get determinant value. So ABCD, which is equal to AD minus BC, should be different than 0. So AD minus BC is equal to 1 times plus I minus I times 1. So AD minus BC is equal to plus I or 2I different than 0. So f is a Mobius transform, or t of z if you want, is a Mobius transform. Find the image under f of the real line R within C. Since the image is of the real line, then the imaginary part of z is equal 0 and z equal x. So f of z is equal to x minus I divided by x plus I, equal, we multiply by the conjugate, both the numerator and the denominator, x minus I squared divided by x plus I times x minus I, equal x squared minus 2ix plus 1 divided by x squared plus 1. This can be broken down into x squared plus 1 divided by x squared plus 1 plus I times minus 2x divided by x squared plus 1, equal 1 plus I times minus 2x divided by x squared plus 1, with 1 being the real part and minus 2x divided by x squared plus 1 the imaginary part. So f of z can be rewritten in the form of u plus iv, with u equal 1 and v equal minus 2x divided by x plus 1. But anyway, it's not our focus. So in order to find the image of t of z in the real line, on the real line, t of z modulus is equal to x minus I modulus divided by x plus I modulus, equal square root of x squared plus 1 divided by x squared plus 1 equal 1. So the image is actually a unit circle of radius 1. Find the inverse transform. So we simply place instead of t, z, w, and we need to find w in respect of z. W equals z minus I divided by z plus I. So wz plus wi, okay, you multiply the extremes, is equal to z minus I. Hence wz minus z, so the z components on one side and the ones without z on the other. Wz minus z is equal to minus wi minus I. So f minus 1 w equals z is equal to minus wi minus I divided by w minus 1. We multiply both the numerator and the denominator by minus 1. So it gives us wi plus I divided by minus w plus 1. A equal 1, b equal minus I, c equal 1, and d equal plus I. So f minus 1 w is equal to minus wi minus I divided by w minus 1. We multiply by minus 1 both the numerator and the denominator. We get wi plus I divided by minus w plus 1. Or you can apply the formula that we've seen before with a equal 1 in the first tz, of course, b equal minus I, c equal 1, and d equal plus I, which is f minus 1 of w is equal dw minus b divided by minus cw plus a. F of z is equal to z plus 3 divided by z plus 4. Okay, you can solve this one also. Prove f of z is a Mobius transform. Determine the image of point z equal 1. Find the fixed points of f, which are the points for which z would be equal to f of z, and find the inverse transformation. You can pause the video and try at it yourself before coming back. Prove f of z is a Mobius transform. F of z is a Mobius transformation if for f of z equal az plus b divided by cz plus d, of course it needs to have this following standard form, the determinant of the matrix ABCD, which is equal to AD minus BC, should be different than 0. So determinant of 2, 3, 1, 4 equal 2 times 4, which is 8, minus 3 equal 5, different than 0. Then f of z is a Mobius transformation. Determine the image of point z equal 1. We simply replace z by 1 in f of z. So for z equal 1, f of z is equal 2 times 1 plus 1 divided by 1 plus 4 equal 3 divided by 5. Find the fixed points of f, or points where z equal f of z. You replace f of z by z. So z is equal to 2z plus 3 divided by z plus 4, which gives us the polynomial z squared plus 2z minus 3 equals 0. Okay, because we moved 2z plus 3 from right to left, so you get z squared plus 4z minus 2z minus 3 equals 0, or z squared plus 2z minus 3 equals 0. We need to find the roots for this equation. So this is a polynomial equation of the form az squared plus bz plus c equals 0. The discriminant is given by b squared minus 4ac, which is equal to 2 squared or 4 minus 4 times minus 3 equals 16. And z, the root, which is 2 roots, is equal minus b plus minus square root of delta divided by 2a. z1 is equal minus b minus square root of delta divided by 2a equal minus 6 divided by 2 equal minus 3. z2 is equal to minus b plus square root of delta divided by 2, which is minus 2 plus 4 over 2 equal 1, which is 2 divided by 2 equal 1. The fixed points are, as a result, z1 equal minus 3 and z2 equal 1. Find the inverse transformation. You simply place instead of f of z w, and we need to find z in respect of w. So w is equal to z plus 3 divided by z plus 4 equal wz plus w4 equal 2z plus 3, which gives us wz minus 2z equal 3 minus 4w. So f minus 1 of w is equal to z equal 3 minus 4w divided by w minus 2. Let f of z be equal to e to the power of z. Describe the image of infinite horizontal strip s equal z equal x plus iy within C for y between 0 and pi under the map of f of z equal e to the power of z. Given z is equal to x plus iy, then f of z is equal e to the power of z, or e to the power of x plus iy equal ex multiplied by cosine y plus I sine y. The image is then f of x is equal to w within C, w is equal ex cosine y plus I sine y for x within R, y between 0 and pi. As x goes to minus infinity, w becomes e to the power of x, okay, which is e to the power of minus infinity or 0. As x goes to plus infinity, w is equal to e to the power of infinity, which is the main component, so which is infinity. Okay, now for y within 0 and pi, we will check argument w is between 0 and pi. So argument of w is between 0 and pi. Finally, s is equal to imaginary part of z between 0 and pi is mapped by f of z equal e to the power of z onto the upper half disk or half plane, which is between 0 and pi on the upper plane, okay, above the real axis. So excluding the real axis, f of s is equal w, where argument of w, or the angle, is between 0 and pi, the upper half disk. Harmonic functions. A harmonic function is a twice continuously differentiable function uxy that satisfies Laplace's equation, given by delta u equal second partial derivative of u in respect of x plus second partial derivative of u in respect of y, equal 0. It should be equal to 0. U is harmonic if its second partial derivatives exist and the Laplacian is 0. In other words, and intuitively, the function is neither increasing nor decreasing, it is repeating itself. This is what it means that the second partial derivatives summed up together give us 0. So the function is not going anywhere. It's like the concavity of the function over x and y is up and down simultaneously, so the sum of these concavities give us 0. The overall sum of the function give us 0, or the tangents. Real parts of an analytic function given by f of z is equal to uxy, real part is uxy, are harmonic because if f of z is analytic, which means it is differentiable, then uv both satisfy Laplace's equation with delta u equals 0 and delta v equal 0. Let's talk about mean value property. The mean value property is a fundamental characteristic of harmonic functions. It postulates that the value of a harmonic function at a point is equal to the average of all the surrounding values within any circle centered around that point. Suppose a uxy is a harmonic function on an open domain D in R square, given a closed disk of radius r centered at z0, brz0, is contained in the disk. The mean value is two-dimensional, so uz0 is given by 1 divided by 2 pi integral from 0 to 2 pi uz0 plus rei theta d theta. This mean value property is given by uz0 equal 1 divided by pi r square integral within the disk brz0 and centered by z0 of uz dx dy, meaning that the value at the center equals the average of the entire disk. For 3D and higher dimensions, ux0 is equal to 1 divided by delta or partial br in modulus integral through the entire area of ux ds. Br x0 is a ball of radius r, and partial br x0 is its boundary, which is the sphere. Example, given f of z is equal to z squared, find the mean value at a disk centered at z0 equals 0 with a radius r. Of course, you can pause the video and try to solve it first. So, if f of z is analytic in a region containing the closed disk D, then Cauchy's integral test applies, which is f of 0 is equal to 1 divided by 2 pi I integral for z minus z0 equal r f of z divided by z minus 0 or z0 dz. Again, as a reminder, for f of z to be analytic in this region, f of z0 should be equal to 1 divided by 2 pi I integral when z minus z0 equal r f of z divided by z minus z0 dz. Let's examine f of z0, which is f of 0. F of 0 is equal to 0 squared, which is equal to 0, and 1 divided by 2 pi I integral f of z divided by z minus z0, which is z squared divided by z minus 0. It is equal to z squared divided by 2 between 2 pi and 0. 2 multiplies the denominator outside, so it is equal to 1 divided by 4 pi I z squared between 2 pi and 0 equal 4 pi squared divided by 4 pi I equal pi divided by I, which is different than f of z0. Since Cauchy's integral formula, CIF, in other words, fails the test, then f of z is not analytic at z equal 0. Let's test if f of z is harmonic. So the form that we need is f of z is equal to uxy plus ivxy. z squared is equal to x plus iy squared equal x squared plus 2ixy minus y squared, which gives us x squared minus y squared plus I 2xy. That's the real part and that's the imaginary part. So uxy is equal to x squared minus y squared and vxy is equal to xy. Delta u is equal to the second derivative of u in respect of x plus second derivative of u in respect of y, which is equal to x, the first derivative, then plus 2, second derivative in respect of x, minus 2y, then minus 2, the second derivative. 2 minus 2 equals 0, so delta v is equal to 0. Then f of z is both differentiable and harmonic, although it wasn't analytic. Let's find the mean value, which stipulates that the average of the entire disk is equal to the value of f at the center, or f of z0. Mean value is given by ux0, y0 equal 1 divided by 2 pi integral from 0 to pi uz0, which is 0, plus rei theta d theta equal 1 divided by 2 pi integral from 0 to 2 pi ux0 r cosine theta, y0 plus r sine theta d theta. uxy is equal to x squared minus y squared. And when we transfer from Cartesian coordinates to polar coordinates, x becomes equal to r cosine theta and y equal r sine theta. You replace them within the ux0, y0 down below, so you get 1 divided by 2 pi integral from 0 to pi r square cosine square theta minus r square sine square theta d theta. ux0, y0 is equal to 1 divided by 2 pi integral from 0 to pi r square, which can be taken to the outside as a common factor since it is a constant, multiplied by cosine square theta minus sine square theta d theta. Going back to trigonometric identities, and you need to memorize this formula, cosine a plus b is equal to cosine a cosine b minus sine a sine b. For a equal b equal theta, you see that cosine 2 theta, which is a plus b, is equal to cosine square theta minus sine square theta. So we can replace these two by cosine 2 theta. This is how we solve a cosine related integral. So ux0, y0 is equal to r squared, we move it to the outside, divided by 2 pi integral of cosine square theta minus sine square theta, which is cosine 2 theta d theta. So ux0, y0 is equal to r squared divided by 2 pi integral from 0 to pi cosine 2 theta d theta, which is equal to 1 divided by 2 sine 2 theta between 2 pi and 0, which is equal to 0. So r of z, or the real part of z, is equal to 0, equal ux0, y0, equal f of 0, by the way. As a result, the complex function satisfies the mean value property. Another one shows that f of z is equal to ln square root x squared plus y squared is harmonic in C, that's the first question. Then that it satisfies the mean property value for any radius except r equal 0. If f of z is harmonic, then it satisfies Laplace equation, which is delta u equal second partial derivative of u in respect of x plus second partial derivative of u in respect of y should be equal to 0. F of z is a composite function because it is made of the logarithm ln, and within ln we have another one, which is square root of x squared plus y squared. So f of prime of z, which is u by the way, is equal to u prime times f prime u. This is the chain rule in derivation. So ln u prime is equal u prime times ln prime u equal u prime divided by u. For the second derivative, since we get from the first a fraction, u divided by v, u being the numerator and v the denominator, prime is equal to u prime v minus uv prime divided by v squared. Derivative of f in respect of x is equal to the derivative of square root x2 plus y2 multiplied by 1 divided by square root x2 plus y2, which is equal to x divided by 2 square root of x2 plus y2 multiplied by 1 divided by square root x2 plus y2, which is the chain rule, equal x divided by x2 plus y2. The second derivative of f in respect of x is equal to u prime v minus uv prime divided by v squared, which is 1 times x squared plus y squared minus u v prime, or x, times derivative of the denominator, which is 2x, divided by x squared plus y squared squared, equal y squared minus x squared divided by x2 plus y2 to the power of 2. Let's get the derivative in respect of y. So f prime z in respect of y is equal to u prime times 1 divided by u, which is 2y divided by 2 square root x2 plus y2, multiplied by 1 divided by square root x2 plus y2, equal y divided by x squared plus y squared. The second derivative in respect of y is equal to u prime v minus uv prime divided by v squared, is then equal to u prime v, or 1 times x2 plus y2, minus uv prime y times 2y divided by v squared, or x2 plus y2 squared, equal x squared minus y squared divided by x2 plus y2 squared, equal second partial derivative of u in respect of y. We place back these two values in Laplace equation, which is delta u is equal second partial derivative of u in respect of x plus second partial derivative of u in respect of y, equal y squared minus x squared plus x squared minus y squared divided by x2 plus y2 squared, which is equal to 0. Hence, delta u is equal to 0. As a result, f of z is harmonic since it is analytic, differentiable, and derivable twice. Let's prove it satisfies the mean property value for any radius except r equal 0. fx0 y0 is equal 1 divided by 2 pi according to the mean value theorem, integral from 0 to pi fr ei theta d theta, z0 equals 0 in such case, with r ei theta equal r cosine theta r sine theta. X should be replaced by r cosine theta and y by r sine theta. These are the polar coordinates. fx0 y0 is equal to 1 divided by 2 pi integral from 0 to pi ln square root of x squared plus y squared, which is r squared cosine squared theta plus r squared sine squared theta d theta. R can be removed outside of the square root, so what remains is cosine squared theta plus sine squared theta, which is 1, equal 1 divided by 2 pi integral from 0 to pi ln r d theta, which is equal ln r divided by 2 pi for theta between 2 pi and 0, equal ln r. Proving it satisfies the mean property value at any radius except r equals 0. So fx0 y0 equal ln r. Let's check the limit for fx0 y0 when r approaches 0. So for r equals 0, limit f of z r going to 0 is equal to minus infinity, so the mean value principle is satisfied for all values of r except when r is equal to 0. It is where the function blows up to minus infinity. Another exercise, f of z is equal to the imaginary part of z equal to xy. Prove that f of z is harmonic, that it satisfies the mean value property around the origin. Let's get the second and first derivative of fz in respect of x and in respect of y. f prime z in respect of x is equal to y. f second z in respect of x is equal to 0. f prime z in respect of y is equal to x, f second equal to 0. So delta f equal second partial derivative of f in respect of x plus second partial derivative of f in respect of y equal f second zx plus f second zy equal 0. As a consequence, or as a conclusion, f of z is harmonic. Let's prove that it satisfies the mean value property around the origin, so around 0. fx0y0 is equal to 1 divided by 2 pi, integral from 0 to pi, f of z0, which is the origin, so z0 is equal to 0, plus rei theta d theta, equal 1 divided by 2 pi, integral 0 to pi, fr cosine theta r sine theta. You replace x by r cosine theta and y by r sine theta d theta. fx0y0 is equal to 1 divided by 2 pi, integral from 0 to pi, 2r squared times cosine theta times sine theta, which is equal to r squared divided by pi, because we've removed the constant parts to the outside of the integral, equal r squared divided by pi, integral from 0 to pi, cosine theta sine theta d theta. Going back to trigonometric identities, we know that sine a plus b is equal to sine a cosine b plus cosine a sine b. Sine a minus b is equal to sine a cosine b minus cosine a sine b. Let a equal b equal theta, then 2 sine theta cosine theta by adding the equations is equal to sine 2 theta. As a way to memorize it, remember that sine couples up with a different partner, so to speak, and the sign does not change. So sine a plus b is equal to sine a cosine b plus cosine a sine b. As for sine a minus b, sine couples up with cosine on both sides and the minus is preserved. Now, how we've gotten the final relationship or equation? We've added up both of the equations, the upper one and the lower one, which gives us 2 sine a cosine b, okay, which is 2 cosine theta, sine theta in our case, is equal to sine 2 theta plus 0, because sine a minus a or sine theta minus theta is equal to 0. This is how we've gotten that 2 sine theta cosine theta is equal to sine 2 theta. Hence, the sine theta cosine theta would be equal to sine 2 theta divided by 2. fx0y0 is then equal to r squared divided by 2 pi of integral from 0 to pi sine 2 theta d theta, because sine theta cosine theta is equal to sine 2 theta divided by 2, as you remember. Okay, the 2 has been removed to the outside, which is equal to integral of sine 2 theta gives us minus 1/2 cosine 2 theta. So it is equal to minus r squared divided by 4 pi cosine 2 theta between 2 pi and 0. This is equal to minus r squared divided by 4 pi times cosine 4 pi minus cosine 0. And 4 pi and 0 are the same angle, except 4 pi is 2 rotations away around the center. Equal minus r squared divided by 4 pi times 1 minus 1 equals 0, which is equivalent to the real part of f of z at z0. Okay, conclusion, it satisfies the mean value property. Now let's talk about boundary value problem in a disk. So, retrieving back the harmonic function theorem, a harmonic function is a twice continuously differentiable function, uxy or uz, where z is equal to x plus iy, that satisfies Laplace equation again, which is delta u is equal to the second derivative of u in respect of x plus second derivative of u in respect of y. Both of them should give us 0. Let uz be harmonic in the unit disk D equals z for modulus z less than 1 and continuous on the closed disk D bar, with boundary values prescribed on the unit circle. Go find ur theta in the disk if the values on the boundary u1 phi is equal to f of phi are known. This is the point of what we've been explaining before, okay? We want to arrive to Poisson integral formula in a unit disk. So let U be harmonic in the unit disk with modulus Z less than 1 and continuous on the boundary. Then for R between 0 and 1, theta between 0 and 2 pi, UR theta is equal to 1 divided by 2 pi, integral from 0 to pi, PR theta minus phi, f of phi d phi, where f phi equal U1 phi, it is the boundary data, and PR theta is the Poisson kernel, which is equal to 1 minus r squared divided by 1 minus 2r cosine theta plus r squared. The value of the harmonic function at an interior point r theta is a weighted average of the boundary value f of phi, where the weights depend on distance via the Poisson kernel. So this is what this theorem is about. UR theta is equal to 1 divided by 2 pi, integral from 0 to pi. This is the average value, by the way. PR theta minus phi, f phi d phi. For the upper half plane H, where z equal x plus iy, y greater than 0, the Poisson integral is uxy is equal to 1 divided by pi, integral from minus infinity to plus infinity, y divided by x minus t squared plus y squared, f of t dt. Ft is the boundary value on the real axis, and the kernel in such case is equal to y divided by x minus t squared plus y squared, which is also a probability distribution. It is called Cauchy distribution. Now let's talk about Fourier series, because here they come in handy, since Fourier series deals with periodic functions. Another name for periodic functions is harmonic functions. Any periodic function f of x with period 2 pi can be expressed, as Fourier stipulates, by the following. F of x is equal to a0 plus sigma n equal 1 to infinity of an cosine nx plus bn sine nx. a0, the first term, is given by 1 divided by 2 pi, integral from minus pi to plus pi fx dx, which is a half rotation. An is equal to 1 divided by pi, integral from minus pi to plus pi fx cosine nx dx, and bn equal 1 divided by pi, integral from minus pi to plus pi fx sine x n dx. Okay, the reason for that is because you have cosine occupying half of the period and the sine occupying the other half. Now the reasoning or the concept with that theory is that any periodic function can be broken down into a sum of sine and cosine, which is very important and simplifies any complex function, any intricate function, especially used in digital signal processing, where a random signal can be broken down or converted into a sum of sine and cosine harmonics. Based on Fourier expansion, let's say you have a function integral from 0 to pi PR theta minus t. This is always within the formula, but what changes is f of phi d phi. Okay, so PR theta minus t cosine nt times dt. This is equal, based on Fourier expansion, to r to the power of n cosine n theta. Okay. Exercise. Let u EIT is be equal to sine 3t, be a function defined on a unit circle, modulus z equal 1. Use the Poisson integral formula to find the harmonic extension UREI theta inside the unit disk with modulus z less than 1. Integral from 0 to pi PR theta minus t sine 3t dt is equal to integral from 0 to pi 1 minus r squared divided by 1 minus 2r cosine theta minus t plus r squared sine 3t dt. Now this one is unsolvable, okay, but through an approximation, and this is given, okay? You don't need to think on how we've gotten that. So this resolves into replacing the entire integral by r to the power of n, with n is the angle, okay, multiplying t, sine nt, which is 1. Okay, the modulus is 1, as we already know. So it is 1 to the power of 3 times sine 3t, because on the inside of this sine you have 3 times t, so n equal 3. So 1 to the power of 3 times sine 3t equals sine 3t. Let f of x be equal to 1 for x between minus pi and 0, and minus 1 for x between 0 and pi. This is an odd function which is symmetric in respect of the origin, hence the term to develop is the sine, because the sine is symmetric also according to the origin. Bn is equal to divided by pi, integral from 0 to pi fx sine nx dx, equal minus 2 divided by n pi minus cosine nx between pi and 0, equal 4 divided by n pi. Okay, because the integral of sine nx dx is equal to minus cosine nx, and f of x is equal to 1. fx is equal to sigma n equal 1 to infinity bn sine nx. So f of x is equal 4 divided by pi sine x plus 1 divided by 3 sine 3x plus 1 divided by 5 sine 5x, etc. The argument principle with Rouchet theorem. Okay, so this theorem and concept is used to locate zeros and poles for holomorphic or analytic functions. Let f of z be a meromorphic function, which means it is analytic except for isolated poles on a domain D, and let C be a positively oriented and simple closed contour within D, such that f of z has no zeros and poles on C. F is meromorphic inside and on C. Then 1 divided by 2 pi I integral f prime z divided by fz dz is equal to n minus p, where n is the number of zeros of f inside of C, zeros are the roots for the numerator, and p is the number of poles. F prime of z divided by fz measures how much the function rotates around 0. The integral computes the change in the argument of f of z as z traverses the contour, so it gives us how many times f of z moves around the origin as z does around C. Rouchet's theorem. It helps us find how many zeros a function has inside a closed contour without having to solve the equation. This comes in handy when dealing with complicated unsolvable polynomials. So let f of z and g of z be complex valued functions that are analytic, differentiable everywhere, on and inside a contour gamma, and suppose f of z minus g of z in absolute value is less than f of z for all z values within gamma. Then fz and gz have the same number of zeros, counted with multiplicity of course, inside gamma. In other words, adding a small analytic function to another one does not change the number of zeros inside the region. Exercise. Using Rouchet's theorem, find how many zeros the following polynomial has inside the circle of modulus z equal 1. F of z is given by z to the power of 7 plus 5z squared plus 10. Let g of z is equal to z to the power of 7, h of z equal to 5z squared plus 10. So we broken down basically f of z into two functions or subfunctions, gz equal z7 and h of z equal 5z squared plus 10. Modulus gz is equal to z to the power of 7, modulus is equal to 1, h of z should be greater than or equal to 10 plus 5z squared, equal 10 plus 5 for z equal 1, which is 5. So gz is less than h of z on z equal 1. Hence, according to Rouchet's theorem, f of z and h of z have the same number of zeros inside the unit circle. The function h of z equal 5z squared plus 10 has roots at z equal plus minus I square root of 2, which is after solving 5z square plus 10 equals 0, you get 5z square equal minus 10, so z square equal minus 2, which is 2i squared. But both of these roots lie outside of z equal 1. Therefore, h of z has no zeros inside the unit circle, and so f of z also has no zeros inside the same zone, which is circle of radius 1. Use the argument principle to solve 1 divided by 2 pi I integral over z equal to f prime z divided by fz dz. The following function, which is fz, is equal to z minus 1 square times z plus 2 divided by z plus 1 times z minus 3. So we need to get the zeros and the poles. You can pause the video and try to solve it first. Zeros. For z minus 1 square in the numerator, z is equal to 1, which is a 0 of order 2. Modulus z equal 1 is less than modulus z equal 2, so it is inside the circle. For z plus 2 equals 0, z equal minus 2, which is a first order 0. However, modulus z in absolute value is equal to, and this 0 is on the contour, so it's counted outside. Hence, the number of zeros is n equal to, because we have a 0 of the second order. Poles. For z plus 1 equals 0, z equal minus 1 is a simple pole. Z equal minus 1 in absolute value is less than z equal 2, so it is counted inside of the circle. As for the second pole, z minus 3 is equal to 0, z equals 3 is a simple pole. However, z equals 3 is greater than z equal 2, so it is outside of the circle. Hence, p is equal to 1. So, to apply the formula for the argument principle, 1 divided by 2 pi I integral for gamma z equal to of f prime z over f of z dz is equal to n minus p, which is 2 minus 1 equal 1. Another exercise uses the argument principle to solve 1 divided by 2 pi I integral for gamma when z equal 2, or for z equal to modulus f prime of z divided by f of z dz for the following function. F of z is equal to z square minus 1 square divided by z times z minus 3. Zeros. At first, z square minus 1 square in the numerator can be broken down into z minus 1 times z plus 1 square. We have 4 roots. So z equal 1 is less than z equal 2, it is inside. Z equal minus 1, which is less than z equal 2, also inside. And also you have double roots. So z1, z2 equal plus minus 1, and z3, z4 equal plus minus 1, because it is squared. So we have 4 zeros. As for the poles, you have z equals 0 and z equals 3, two simple poles. Now for z equals 0, it is less than modulus z equal 2, so counted inside of the circle. For z equals 3, it is a simple pole, however it's greater than z equal 2, so it is outside of the circle. Applying the argument principle, 1 divided by 2 pi I integral over gamma modulus z equal to f prime z over f of z dz is equal to n minus p, which is 4 minus 1 equal 3. Determine using Rouché's theorem how many zeros the following function has inside the circle of z equal 1 modulus z. F of z is equal to z to the power of 5 plus 4z3 plus 1. Let's break down f of z into two simpler functions, gz equals z5 and h of z equal 4z3 plus 1. G of z equal 1 is equal to 1, and h z equal 1 is equal to 4 plus 1, which is 5. So g of z is less than h of z, with f of z equal gz plus h of z. As a conclusion, f of z and h of z, the larger function, have the same number of zeros. Let's solve h of z. So z to the power of 3 is equal to minus 1/4. Okay? When you place 4z3 plus 1 equals 0. It has 3 roots. So z3 is equal to minus 1 divided by 4. Z is equal then to 1/4 to the power of 1/3, which is the third root of 4, e to the power of I, pi divided by 3 plus 2k pi. Okay? Because it rotates, and at each rotation it can have a different root. 2k pi for k equals 0 or k equals 1. This is the nth rotation, full rotation around the center. So k equals 0, 1, 2. Z1 is equal to 1/4 to the power of 1/3 ei pi divided by 3 for k equals 0 less than 1. Z2 is equal to 1/4 to the power of 1/3 ei pi divided by 3 plus 2 pi k equal 1 is equal to 1/4 ei 7 pi divided by 6, and Z3 is equal to 1/4 to the power of 1/3 ei pi divided by 3 plus 4 pi equal 1/4 ei 13 pi divided by 3, also less than 1. So we have 3 cubed roots different by angle. Now let's present some advanced topics such as analytic continuation. Analytic continuation allows the extension of the domain of a complex function beyond where it was originally defined. Let f of z be analytic, holomorphic on an open set U within C, and analytic continuation of f of z to a larger domain V greater than U is a function f of z such that, capital F here, f of z is analytic on V the same way that lowercase f is analytic on U, and f of z is equal to f of z for all z that are within U, within the subregion. In other words, f of z extends f of z lowercase on V while preserving analyticity and complies with it where both are defined. Schwarz reflection theorem. Schwarz reflection theorem allows us to extend an analytic function over the real axis, a line, or an analytic arc under specific conditions. Suppose f of z is a complex function analytic in a domain D in the upper half plane, and suppose f extends continuously to the real axis, D intersect R, f of x is within R within the real ensemble for all real x in D intersect R, then f of z is equal to f of z, lowercase f of z, if imaginary part of z is greater than or equal to 0, and f of z bar if the imaginary part of z is less than 0. So this is analytic in D U D bar, where D bar is equal to Z bar, and Z belonging to D is the reflection of D across the real axis. Finally, Schwarz-Christoffel exercise. Use the Schwarz-Christoffel formula to find the conformal map from the upper half plane H equals Z within C, imaginary of Z greater than 0, onto the interior of a triangle with vertices at W1 equals 0, W2 equal 1, W3 equal 1 plus I, taken in counterclockwise order. The formula for Schwarz-Christoffel is f of z is equal to a plus c, integral for the product, by the way a and c are arguments to be found, of p. P here is the product of the different arguments, which are t minus zk. Zk are a set of z1, z2, z3 that map w1, w2, and w3 to the power of beta k. Beta is actually alpha divided by p minus 1, with alpha respectively for each z is actually the angle at that corner, the interior angle of the polygon, so to speak. Okay, so imagine w1 equals 0, w2 equal 1, w3 equal 1 plus I. We map them into z1, z2, z3. For the first one, you have the angle is pi over 2, 90 degrees, and the remaining angles are pi over 4. So because it is a rectangular triangle, okay, so one of the angles, the first angle is 90 degrees, and the remaining angles are pi over 4. So beta 1 is equal to pi over 2 divided by pi minus 1, which is minus 1 divided by 2. Beta 2 is equal to minus 3 divided by 4, because one of the angles is actually 3 pi divided by 4, and the other angle is pi over 4. Okay, so minus 3 divided by 4 minus 1 divided by 4. So the integral becomes a plus c integral 4. T plus 1, which is t minus 1, to the power of beta 1, which is minus 1 half, times t minus 0, which is t, to the power of minus 3/4, times t minus 1 to the power of minus 1/4, t minus 1, which is t minus z3, to the power of beta 3, which is minus 1/4 dt. So a and c are determined using boundary conditions to get the angles between, for example, one is between 0 and pi divided by 2, etc. Okay, this is more of a conceptual. We're not going very deep in that. Exercise. Find the Schwarz-Christoffel transformation that maps the upper half plane onto the interior of a semi-infinite strip bounded by the real axis from 0 to infinity, a vertical segment from 0 to I pi, and the line segment from I pi to plus infinity I pi. That is, map the upper half plane onto the region W equal x plus iy within C, x greater than 0, and y between 0 and pi. We choose 3 arbitrary points. You have z1 equal minus 1, z2 equals 0, and z3 equal 1. Okay, within the circle. So, and belonging to the upper plane as well. For z0 or for z2 equals 0 and z3 equal 1, alpha 2, 3 is equal to pi divided by 2. Why? Because this is the upper plane, and the real axis, whether at 0 or 1, is 90 degrees away from the upper half plane of the y-axis or the imaginary axis. Now, so beta 2, 3 is equal to alpha divided by pi minus 1, which is minus 1 half, okay? Pi over 2 divided by pi minus 1 give us minus 1 half. For z1 equal minus 1, which can be written as I square. So it is on the same plane of the upper half plane, so the angle is 0. Hence, beta 1 is equal to 0 minus 1, which is minus 1. So f of z is equal to a plus c integral of the product of t minus zk, zk being z1, 2, 3, the arguments, to the power of beta k, beta for each z. So integral of t to the power minus 1 divided by 2, this is for actually t minus 0, okay? And the value of beta is minus 1 half times t minus z3, which is t minus 1 to the power of minus 1 half, times t plus 1, which is t minus minus 1, or t plus 1, to the power of 0, because the angle is 0, which gives us 1. Integral of 1 divided by square root of t times t minus 1 dt equal minus I arc sine 2t minus 1. Find the Schwarz-Christoffel transformation that maps the upper half plane onto the interior of a rectangle with vertices at w1 equals 0, w2 equal 2, w3 equal 2 plus I, w4 equal I. Choosing z points, we choose minus 1, 0, 1, and infinity. Now the angle for the 4 of them, for the 4 corners, is pi over 2, because we have a rectangle with each angle equal to 90 degrees. So the values are given by z1 equal minus 1, 0, 1, infinity, with k from 1 to 4 having the same beta. Value of beta is equal alpha divided by pi minus 1, which is minus 1 half. So the integral gives us t minus 1 to the power of minus 1 divided by 2, which is t minus z3, times t plus 1, or t minus minus 1, to the power of minus 1 half, times t minus 0 to the power of minus 1 half dt. z4 does not count. z4 at infinity, the angle is 0. Which gives us f of z is equal to a plus c integral of 1 divided by square root t minus 1 times t plus 1 times t, or 1 divided by square root t squared minus 1 times t. We place or we suppose t equal sine theta, then dt equal cosine theta d theta. And based on that, we try to solve the integral. It's a little bit intricate, okay? But using that methodology, we get to 1 divided by I integral of 1 divided by square root of sine theta d theta. Another exercise, find the Schwarz-Christoffel transformation that maps the upper half plane onto the interior of an equilateral triangle with vertices w1 equals 0, w2 equals 2, and w3 equals 1 divided by 2 plus square root of 3 divided by 2i. Now for this triangle, since it is equilateral, then for each and every point we have the same internal angle, which is pi over 3 or 60 degrees. So alpha k for both 1, 2, and 3, not 4. We have the same internal angle, which is pi over 3. So beta, which is equal to alpha divided by pi minus 1, gives us pi over 3 divided by pi minus 1 equal 1/3 minus 1 equal minus 2 divided by 3. And for the arbitrary points, we choose the following points, which are also called pre-vertices. z1 equal minus 1, z2 equals 0, and z3 equal 1. Now let's apply the formula of Schwarz-Christoffel, which is fz is equal to a plus c integral of the product of the set t minus zk to the power of beta k. Pi acts like a sum, you know, the sum symbol, the sigma symbol. Here, the capital pi means the product of components instead of the sum. Applying the formula, we get integral of t minus z1, which is t minus minus 1, or t plus 1 to the power of minus 2/3 times t minus 0 to the power of minus 2/3 times t minus 1 to the power of minus 2/3 dt. So f of z is equal to c integral of 1 divided by t times t plus 1 times t minus 1, all of them to the power of 2 divided by 3, plus a. Thank you so much for watching. I hope you enjoyed this lecture or this tutorial, whatever you want to call it. I hope it was beneficial, and God bless you.